Let me just
Welcome to the 2022 NASA STEM Enhancement in Earth Science High School Internship Science Symposium. SEAS is a collaboration between NASA, the University of Texas at Austin's Center for Space Research, and NASA Texas Space Grant Consortium. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and with space contractors, and have been hired by NASA to work on missions such as Europa. In 2022, we received almost 1,100 applications, and we selected 260 10th and 11th grade students as participants who were assigned to 18 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science modules, Python coding, and project-specific work prior to starting their project. Interns heard from 12 different NASA subject matter experts that highlighted NASA missions, opportunities, and careers during this internship. You are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller and myself, Margaret Baggio, the managers of the SEAS program, welcome to NASA SEAS 2022. Today, we will have 12 team and individual project video presentations. We will divide the afternoon into 3 sessions with 2 20-minute breaks, one at 2:10 and one at 4:05. Project video presentations will either be 5, 10, or 20 minutes in length, followed by questions and answers. Please post your questions on the slido.com website and use the code SEES, S-E-E-S 2022. Here is our schedule for the day. We will have presentations by team members, followed by a 5-minute Q&A. We will invite each team presenting to turn on their cameras and their microphones to answer the questions posed by those of you who are listening. During the 20-minute break, we invite you to watch the video highlights of the student intern produced products as part of their Earth and Space Science and Python projects. Our first presentations are by interns in the air quality group. Students conducted intensive research into air quality with the Air Quality Initiative group hosted by the Globe Mission Earth team and NASA Langley Research Center. Data will be shared on Globe's visualization system, a cloud-based geographic information system, GIS, of citizen science data. Students chose research projects based on their particular interest within the science of air quality. Thanks to their mentor, Sarah Mears-Riak, for her guidance and her expertise. We will have 2 individual presentations from the air quality group, followed by a Q&A. Our first presentation is varying ozone trends in relation to environmental health presentation.
Hello, my name is Jonathan Krabji, and I'm a 16-year-old NASA SEAS intern for summer 2022. This summer, I was fortunate enough to work with experienced mentors and teammates in the Air Quality Initiative group. During my time in this internship, I created a research project on air quality with environmental and health aspects, which is what I'll be presenting to you today. I'd just like to say thank you to all of you in the audience who are watching the symposium and for taking the time to watch my presentation. And with that, I'll now present my research project, which is air quality, varying ozone trend in relation to environmental health. So to let you guys know a little bit more about me, I'm currently a rising junior at Croton High School, and I live in Fredericksburg, Virginia. I live with my parents and have an older brother who's in college. I play travel soccer, and I also played for my high school team this past year. I plan to major in biomedical sciences and hopefully become a medical scientist, which is why my project involves health relations to air quality. In this presentation, I'll go over some background information, the site I use to properly present my data, and my final conclusion for my research project. So between 2016 and 2018, there was a decrease in crop yield in ozone-prone plants such as cotton and peanuts. At the same time, there's been a rise in nutrient deficiency diseases that have led to chronic illnesses. For my research project, I focused on how ozone can affect crop yield, and I then made a relation to nutrient deficiency diseases and secondary complications, such as heart disease, high blood pressure, etc. With my project, I was able to use a website called ArcGIS Story Maps to create a platform that has a record of all my research data analysis. So here's my research question and my hypothesis. My research question is, how does ozone influence agricultural contributors to public health? And my hypothesis is, if different regional areas in the U.S. exert high ozone levels than other regions, then it will cause inadequate crop yield in the same regions that produce those crops, which will most likely lead to spike in nutrient deficiency diseases and secondary complications. So here's my introduction with all the information that I already discussed. And here is a slideshow for the U.S. regional areas based on the EPA, which is the Environmental Protection Agency. So for example, we have the Northeastern region, which has some states like Maryland and Massachusetts. And here are the agricultural areas. So I looked into 3 main crops: soybeans, cotton, and peanuts. So here's the soybean crop area, which is mostly found throughout the middle parts of the United States, as well as some parts in the South and East Coast. We have cotton crop areas, which is spread out throughout the southern half of the U.S., and peanut crop areas, which is between the south central and southeastern parts of the U.S. So I first looked into ozone trends by U.S. regions. According to my hypothesis, the South region should experience low crop yield compared to all the other regions because most of the crop planting and relatively high ozone levels correspond to this region. Based on the data, it's noticeable that the southern region's ozone levels have continuously increased over time compared to the others that only fluctuations in ozone levels. I then looked into crop yield. So typically soybeans, cotton, and peanuts are crops that are most negatively impacted by ozone increase. So soybeans have generally increased over time between 2016 to 2018 and become the most abundant crop produced in the U.S. Cotton has some fluctuations, mainly because of the decrease from 2017 to 2018. I believe this is due to the immense ozone trends in the states and crop areas that produce cotton, so it would cause these weird fluctuations. And peanuts have generally decreased over time, mainly because of the area planted. So in 2017, the area planted was higher than in 2018. Therefore, the reduction was higher in 2017 than in 2018. So normally with my research, I believe that cotton production would be higher than soybean because of its abundant use in the food industry. Cottonseed oil is used in many salad dressings, processed foods, and even served as frying oils in some restaurants. Businesses tend to use cottonseed oil because it's usually cheap and can preserve foods for long periods of time. Peanut oil is also used in restaurants as well, but not as much as cottonseed oil. So with further research, I was able to find that soybean oil was relatively cheap between 2016 and 2018 and even decreased by the end of 2018. However, with cotton, it was very expensive and even increased by the end of 2018. From this, I deducted that the reduction of more soybeans caused prices to be cheaper, allowing for more businesses to buy more soybeans or soybean oil to be used. This trend most likely indirectly caused less cotton to be produced, hence increasing the prices, and fewer companies use them despite its versatility. This concept of cotton would also, I would say, apply to peanuts. So where the nutrient deficiency comes in is that cotton normally has a lot of potassium and peanuts have a lot of magnesium. However, cotton has a toxin called glycosol, which is naturally produced in the plant to protect itself from insects, but harmful for us and other animals to ingest. So when translating this cotton into cottonseed oil, factories and businesses refine it, hydrolyze it, and even bleach the oils in order to create cottonseed oil. Yet, even though it takes out the toxin in cottonseed oil and even the allergic properties of peanut oil, it also takes out their nutrients. And so now people are eating a lot of processed foods with not as much potassium and magnesium as needed. Over the past 50 years, there has been a relatively high increase in concern of potassium and magnesium deficiencies in the US. Therefore, I looked into diseases that related to potassium and magnesium deficiencies. Potassium deficiencies tend to lead to high blood pressure and kidney disease, and magnesium deficiencies lead to high blood pressure, heart disease, and diabetes. As you can see here, between 2016 and 2018, there was a relatively high increase between most of these diseases, therefore generally advocating my hypothesis. For my final conclusion, my hypothesis was generally correct, but more minor factors were needed to be implemented to correlate my original aspects. For instance, the prices of crops were not in my original research, where I simply focused on other trends, crop yield, and nutrient deficiencies. However, this factor was needed in order to properly correlate my topics, but did not reflect in my initial inferences. So for my methodology part of my project, I first looked into a series of live websites that could track the quality of atmosphere and other environmental factors such as heat. When I saw a prevalence of extreme temperatures in the southern region, it gave me the idea of relating some sort of greenhouse gas to crop yield and disease, which were topics that I was previously interested in. I looked through many medical articles and agricultural documents, and I could finally correlate all of my data and information together with my research question hypothesis. As a NASA intern, I generally had a great experience in Austin, Texas. I was able to create a successful research project that incorporated my interest from the medical field, and I got to meet new people that were different yet had similar interests to me. I was able to group an amazing group of people who were very lively and I were a blast to have around. I again would like to thank my mentors for their experience and guidance that they have given me in making this project. As well, I'd like to especially thank my teammates for without their adjustments and suggestions for this project would not have been as solid as it could be. I again thank you all for watching and hope you enjoy the rest of this presentation from our air quality team, as well as other groups presenting in this symposium. Hello, my name is
Hello everyone, I am part of the Air Quality Initiative team, and my research is mainly comparing purple air sensors to EPA monitors. She Cadence Palmer Hunsie, she Mashkalende Anshti. My name is Cadence Palmer. I am currently a rising junior from Mescalero, New Mexico, and I am part of the Mescalero Apache tribe. The question I was interested in was, does the data collected from air quality instruments diverge from each other? Before starting my research, I hypothesized that data recorded by purple air sensors would report higher values than the EPA monitors in close proximity to one another. At present time, air quality is becoming a huge concern in all areas, especially around the world, mainly because air quality, which is pollution that is intensifying over time. The reason why is due to air pollutants that contain pollutants and particle matter, PM. Ineffective particle matter is insistent on its size, structure, solubility, and potential to manufacture reactive oxygen species. These particle matters can be located on the right side of the screen. In the picture shown is a human hair. On that hair is PM10, represented by the blue circles, and in that blue circle is PM2.5, represented by the small red circles. PM2.5 is known for having a small diameter. It has been publicized that PM2.5 is one of the elements of human death. Researching this topic is important, allowing people a better understanding of how air quality monitors and sensors are produced by the manufacturers to provide people with a better sense of reliable data without providing them with a false sense of security. My intentional goal is to compare a sensor and monitor data. The difference between both is that the sensor is placed at low quality pricing, while the monitor is provided with high quality pricing, allowing me to lead to curiosity if the price of the sensors or monitors have an immense impact on how well the data is collected, or if there are any differences to be noticed. The methods used were first expanding research on PM 2.5 and next observing areas on the maps that can be used for both purple air and EPA. Then accumulate data from purple air and EPA. After that, contrast the specified data. Finally, once specified data is received, results will be provided. The areas I have chosen to work with are Albuquerque, New Mexico, and Sarasota, Florida. Here in the photo on the left is what purple air sensors look like. On the right is what the EPA monitor looks like as well. The results I have received back are the bar graphs that is shown that the average percent difference of PM 2.5 is colored blue. Shows Albuquerque, New Mexico was 141.72 and Sarasota, Florida was 30.49%. Meanwhile, the average AQI difference shown in red for Albuquerque is 138.33% and Sarasota is 32.02%. When it comes to world issues, one factor that can't be ignored is air quality. Working on this project has led to a few difficulties, such as EPA monitors not being in the same location as the purple air sensors. So limitations were made, such as choosing areas within a close distance of EPA monitors and purple air monitors. When this difficulty occurred, it also left an effect on the locations. First, I had an idea of looking more into El Paso, Texas, due to it being close to my reservation and the amount of haze that is visible in the air. Instead, I chose to look into Albuquerque, New Mexico, and Sarasota, Florida. Owing to the fact that when looking for good data, a factor to keep in mind is if the sensor is 100% accurate. The project itself, I wanted it to lean more onto the engineering aspect because of my interest, so I was planning on sharing information on how those sensors and monitors came about, but due to limitations again, I wasn't provided access to gain the blueprints from purple air. In conclusion, the data do diverge from each other, proving that purple air has a lower performance than EPA monitors. My future plans are to continue the work put into this project, expanding it more by possibly listing the components inside the device and looking more in depth at how those devices function, while expanding the number of sensors used just to look more into this project and improve it in the best ways I can. My highlights during SEAS are being in a different environment, surrounded by many amazingly smart people to learn and share knowledge, because that it has motivated me to continue my work in STEM. The challenge I have faced was getting a better understanding of how to convert my data and how to get a better understanding of air quality, also just being homesick. Coping with that has led me to my team members and new friends who have helped and just been there for me every step of the way. I think SEAS has made an impact on the future for the better, such as still bringing excitement for me to enter the mechanical engineering field, not only by sharing my experience back home with my community, but sharing the message SEAS gives me, which is to encourage other kids, especially Native American kids, that if I can do it, they can do it as well. And life has so many beautiful opportunities, besides staying on the reservation to follow your heart, especially if it's in the STEM field. Finally, I'd like to say thank you to the Air Quality Initiative team, my mentors, Nihar Jenga for helping me with my data, and a huge thank you to Texas Space Grant Consortium, Globe Mission Earth Center for Space Research, the University of Texas at Austin, and NASA. Yeah, thank you.
So I would like for Najami and Cadence to please turn on their cameras and unmute themselves. We have several questions. The first one is for Najami. What did you find most surprising about your research?
What I found most surprising was that there's a lot more factors that affect overall in the increase in health. So for example, like I said before, I started simply looking at ozone, crop yield, and nutrient deficiencies and the increase rates in the US, but I had to look into more economic factors over the years to actually properly correlate all my data. So I think that would be the most surprising thing.
Cadence, what advice would you have for other citizen scientists that are researching air quality?
The advice that I would give you is that whenever going into air quality, you may not end up with the results you thought you would have in the beginning, but just continue to research it. And there may be a factor that you missed out, which will be like very helpful towards the end.
That's great advice. Dajami, was there any specific challenge that you faced when you were doing your research process?
This was a pretty big one. So when it was towards the last few days of the internship, and I had all my data correlated and everything. And I was going over with my mentor, and she asked me if how my data really correlated and everything, and if it really made sense. And it looked like my hypothesis wasn't actually correct, like I had stated before. So she wanted to tell me to simply just say how the medical stuff inspired me to look into ozone trends and crop yield. But instead, I looked into other factors like the economic factor that I mentioned before, and that really correlated everything and generally proved my hypothesis.
Great. Cadence, what ideas do you have for sharing what you learned with your peers at home?
The ideas I have is actually I plan on presenting to my whole school as the community, such as elementary through high school. And I want to present what I did and the struggles I faced, but I want to encourage them to do stuff like this as well.
And Dajami, how much do you think that the different uses of cotton and peanuts besides oil production play a role in your results?
I would say that it generally it was kind of significant in a sense, because we all know cotton, you don't see us in every day just eating cotton all the time. And for peanuts, we know that you can also eat those separately and not having to use actual peanut oil. So those are, I guess, other factors I could have incorporated into my research.
And this question is for both of you. We'll let Cadence answer first. If you were going to continue your research project about air quality in the future, what path of research would you take, and what would you be interested in learning more about?
Okay, so at first I wanted to go more in learning about the monitors and sensors themselves, like in the mechanical aspect, because that's where my heart follows. But I couldn't do that due to purple air not allowing me access to the blueprints. So maybe later on, I plan on going more into the mechanical aspects of these sensors, but finding a way around the blueprints. So that's my idea of going more into my research.
Great. Dajami, what suggestions would you have to pursue in your research, something that might take on a little different aspect?
I think the main thing was incorporating more factors into my research project. I believe that there are so many different factors, such as transportation and like CO2 emissions, and even like the consumer likeliness to buy products that have cottonseed and peanut oil. So in the future, I think I'd want to look into more of those very small but significant factors to really make my research project accurate.
Well, I want to congratulate both of you. You have done an amazing job, and I know that I learned a lot. So thank you for participating in SEAS, and thank you for presenting your research. So we are ready for our next group in the Air Quality Initiative, and they will be discussing quantifying the need for more EPA monitor-based databases on correlations between air quality and socioeconomic factors presentation. And then the second one will be on air quality versus health factors.
welcome to our 2022 NASA SEAS experience. Today, we'll be talking with you about our research fun and the future.
Hi, my name is Ishan Das Gupta. I come from Westwood High School, and I plan on going into computer science.
And I'm Nihar Jenga, a rising senior at Vandergrift High School that's interested in environmental studies.
So first, I want to talk a little bit about our research that's titled Quantifying the Need for More EPA Monitors Based on Correlations Between Air Quality and Socioeconomic Factors.
So how did we get here? While we were doing preliminary research to decide what topic to explore, I stumbled across a UN article documenting the horrible situation of Cancer Alley, a region in southeastern Louisiana that is known for its disproportionate exposure to carcinogenic chemicals released by petrochemical industries, and this results in disproportionate health risks for the people in Cancer Alley. So what we wanted to do is look at correlations between socioeconomic data, health data, and air quality data to help find sites like Cancer Alley and report data from them. However, once we ran the correlations, we really weren't able to find sites like Cancer Alley, not even Cancer Alley itself. And so when we looked into the data to see what was wrong, we saw that there weren't even enough EPA monitors in Cancer Alley. So then we shifted our focus, and then we got to the idea that we should look at quantifying the need for more EPA monitors, tackling the issue of not having monitors in the places where they matter. And so while we were thinking about how to quantify this, we were just looking at a literature review just to read up on the topic to get as much background as possible so we could take the next steps. But while I was doing the literature review, I found these articles from like prestigious institutions that showed that there were indeed correlations that did exist that could show sites like Cancer Alley. So from that, I was a little confused because the correlations that we ran were weak while these papers were saying that the correlations were strong. And so once I looked into it further, I realized that's where we could find how we could quantify the need, this gap that exists between existing peer-reviewed research and our correlations that use two different methods of collecting data. And so these are the papers that we use to compare for the literature review with our correlations to get those gaps. And we'll talk about that further in the results.
Okay, but first we need to look at how exactly we conducted this study. So our methodology first includes data collection, and we collected data from mainly three sources, which includes the Census Bureau, SAPI, program of the Census Bureau, and as well as the EPA AQS API using Python. And then we processed said data, and in processing it, we filtered out certain data characteristics of monitors based on, say, certain things like certification and methods. And we also translated units into other units for consistency and clarity when presenting. And then we organized all that data into a single data frame. And then after processing the data, we then could move on to analyzing the data. So we started plotting data on scatter plots, heat maps, bar charts, trend lines. And for all these correlations, we calculated R-squared values so we could compare these R-squared values across graphs. And that leads us to our results. So in our results, we first analyzed the correlation between population and nitrogen dioxide in US counties in order to have a sort of control for our methodology. So we could see just how accurate our methodology was in comparison to the literature review. So if the results of this comparison matches up with the literature review, we would have succeeded. And that's what happened. The R-squared values, which hovered around 0.4 to 0.45, matches up with the results that were presented in the literature review, which shows us that our methodology in calculating this data is correct and can be used correctly to compare with another study.
And so once we established that our methodology was right, given the fact that we also noticed that most of the sensors were in urban areas, and that the literature review that we used compared NO2 to urban population, once we realized that our methodology was correct, we started looking into the places where our correlations really didn't match up. The first thing that we looked at was the correlation between race, specifically percent of the population that was African American versus PM 2.5, which in one of the papers in the literature review showed that there was a significant disproportionate amount of African Americans that were exposed to high levels of PM 2.5. However, the data that we ran from EPA Air Monitor data showed that there's relatively low levels of R-squared, which means that there has to be some sort of a gap between our data that we use and the data that was used in the literature review. This is further reinforced by when we looked at correlations between a certain type of socioeconomic status, poverty rate, versus PM 2.5, comparing that to a paper that indicated that low socioeconomic status tended to have higher levels of air pollutants. And so we didn't just look at PM 2.5 in this case, because the paper did mention that they also use different air criteria. So we looked at PM 2.5, we looked at ozone, we looked at carbon monoxide, we looked at sulfur dioxide, and we looked at nitrogen dioxide. But if you saw while I was scrolling, one thing that you could mention was that we had really low R-square values. Like most of them were below 0.2, which means there's an extremely weak correlation, which completely contradicts what the literature review paper said in saying that low SES or socioeconomic status communities tend to have higher, but this is not what this is showing at all. So again, there's that idea of there's a gap in the data because it's just not matching up with these peer-reviewed, scientifically renowned institutions' research.
Right. And so we started looking at some of the limitations of our study. So one big limitation is that there's a big lack of high quality ground level data in rural areas. So if we take a look at this map, there's a concentration of EPA air quality monitor sites in eastern US, but not so in central US. And that shows that there's a concentration of these sites in urban areas and not so in rural areas. So our study kind of takes an urban perspective, which gives us a biased look. The data is biased, and therefore our results may be limited to that bias. So we are arguing that we need more ground level data on rural areas because other studies, which may be using satellite level data, are getting a bigger picture view, but we need that precise ground level data in more areas. And there's also a lack of high resolution socioeconomic data. And what this means is that around one specific monitor, we don't have all the socioeconomic information around the people around that monitor. So we're losing the trends that could be specifically related to the number on that specific area. We don't have that granular level of socioeconomic data, which would be incredibly useful for new insights.
So conclusion of our study, based on the results, we found that there was a significant difference between our correlations that we ran with EPA monitor data and the correlations that were found through other means such as satellite data in the literature review, which points to a gap in the data. Most likely that is the most plausible reason of difference. But we do want to explore further just to strengthen our case. We want to explore, for example, using more high resolution data, pushing for that more precise, accuracy. And then we also want to look at using purple air sensors, which is another ground level based air quality observation technique other than EPA monitors. Maybe it's a quality thing and not a quantity thing. And then there's also just so many possibilities. We can look at different sectors, health and environment instead of just socioeconomic. And just looking at all of these things would help us paint a better picture of whether or not we need more EPA monitor data. And so these are the references, the papers that we used in the literature review. But enough of that, let's get into how the SEAS experience was fun for us.
Right, so this is our air quality initiative team. We had a blast. They're some of the brightest people I know. We went on so many trips. I enjoyed all the time with them, and these are our mentors.
Yeah, I just want to say thank you so much to our mentors for the project that we did. I mean, we definitely would have not been able to do it without their support and their guidance. Sarah, Janine, Dr. Pippin, Dr. C, they helped us whenever we needed. We always bothered them with questions, and I'm just really grateful that they were there to help us along every step.
And regarding the future, we just have a few words to say. I love the SEAS experience. It taught me how to combine computer science, my passion, with something like collaboration and working with amazing people like Nahar and the rest of my team. And combining computer science and collaboration really is going to impact me in so many different ways. I'm excited. I'm looking forward to the future because of SEAS. So thank you so much.
Similarly, I've learned so much from SEAS. First of all, just looking at research from a different angle. When me and Ishan first ran the data and found that there was like really weak correlations, I freaked out because what a good researcher wants is good correlations, or at least that's what they say. But from C's, I learned that a good researcher is able to turn correlation or no correlation into something significant. And that's what we did. And I'm really grateful for C's for teaching me that lesson. And just in general, C's has been an amazing experience with friends. They're like my new family. We got a lot of new opportunities, and I'm just really grateful for C's giving me everything. And I really think it's going to shape my life, and I'll never forget it. So thank you so much, C's. We're really grateful.
Hello, my name is Allie McCabe, and I'm a senior from Benicia, California, and I'm interested in environmental science.
Hi, my name is Gardenia Liu, and I'm a senior from Austin, Texas, and I'm interested in environmental engineering.
Hi, my name is Audrey Kuo, and I'm a senior from Parsippany, New Jersey. I'm interested in neuroscience. We're a part of the NASA Seas Air Quality Initiative team.
So what defines air quality? Air quality is simply a measure of how clean or polluted the air is. One type of air pollutant is aerosols, which are airborne particles, also known as particulate matter, or PM for short. They are minute solid and liquid particles suspended in the atmosphere, which can come from man-made or natural sources, and can have adverse effects on human health.
We specifically focused on PM 2.5 particles, which are 2.5 microns or less in width. Particles this small, once inhaled, can travel deep into the lungs and can even enter the bloodstream, leading to health problems such as heart attacks and increased respiratory symptoms.
With each of us residing in different states spread out across the United States, our project focuses on our home states of California, Texas, and New Jersey on the county level. As shown in the table, these states have significant demographic differences. California and Texas are much larger than New Jersey in terms of both population and area. New Jersey also has a much higher percentage of urban land use.
Our group was interested in the correlation between PM and public and environmental health. Within public health, we investigated factors such as birth weight and asthma rates. Within environmental health, we examined vegetation health and coverage. This was measured by NDVI, or Normalized Difference Vegetation Index. NDVI gives information on the density of vegetation and is calculated using a mathematical formula determining the ratio of visible and near-infrared sunlight being reflected. We hypothesized that there would be a negative correlation between PM 2.5 levels and NDVI, as well as positive correlations between PM 2.5 levels, asthma rates, and percent low birth weight for all 3 states.
We first examined literature relating each of our factors and PM 2.5 particles to familiarize ourselves with the topic before finding our own correlations. For asthma and low birth weight, there was a positive correlation to PM 2.5, and for NDVI, there was a negative correlation for each of our 3 states.
We collected all of the data and images for all 3 states from the years 2014 to 2018 from the CDC National Environmental Public Health Tracking Network. Next, we compared PM 2.5 to the different chosen factors by importing the data into Google Sheets and generating scatter plots.
For NDVI, the CDC NEPH tracking network did not give data organized by county, but rather by individual census program that averages the census tract values for each county in order to keep the geographic scales consistent. By creating scatter plots that compared each of the factors to PM 2.5, they returned R and R squared values that indicated the strength of the correlation between air quality and the other factors being studied. Values closer to 1 suggest strong correlations, while values closer to 0 signify weak correlations.
Here's a slider that shows 2 animated GIFs. The left GIF shows the average annual PM 2.5 level in California from 2014 to 2018 against a right GIF, which shows the crude rate of asthma hospitalizations on the county level. The hatchmark patterns indicate data that is modeled. As you can see by the rise in blue counties over the 5-year period in California, air quality levels to worsen. When looking at the asthma hospitalizations, the general trend is that over time, across the counties, the rate is seen to decrease. On the right shows a scatter plot showing the correlation between asthma hospitalizations and PM 2.5 across the 5 years. As time progresses, the strength of the correlation decreases, as indicated by the decreasing R values. While correlations between asthma and PM 2.5 on the state level are weak, certain counties prove otherwise, such as Fresno and Imperial County.
The GIF on the left displays monitored and modeled annual PM 2.5 levels for Texas from 2014 to 2018. Many of the counties have hash marks indicating that the data is modeled rather than monitored, which is due to the lack of PM 2.5 sensors throughout parts of Texas. The GIF on the right shows the prevalence of asthma in adults. Since the database we used did not have asthma hospitalization data for Texas, we chose to study the prevalence of asthma in adults instead. Due to data limitations, we were only able to generate a scatter plot showing the correlation between asthma prevalence in adults and PM 2.5 particles for 2018. Similar to that of California, the R and R squared values are low as well, but the counties of Cass, Bruce, and Kennedy seem to have higher correlation values between PM 2.5 and asthma.
The left GIF demonstrates the annual average PM 2.5 levels in each county of New Jersey from 2014 to 2018, while the other GIF displays the age-adjusted rate of asthma hospitalizations per 10,000 population. It is evident from the R and R squared values that New Jersey has a slightly higher correlation than California and Texas do. Both PM 2.5 levels and asthma hospitalizations decreased over the 5-year period, though the correlation remains about the same. The correlation was particularly pronounced for Burlington, Cape May, and Somerset counties.
Across the 5-year period in California, the general trend is that the percentage of low birth weight is seen to increase. The scatter plot shows that the R values between low birth weight and air quality are all close to zero, indicating weak correlations. However, certain counties, including Placer and San Bernardino County, indicate a strong positive correlation. There seems to be no overall trend for correlation coefficients R over time, but the correlation for 2017 is significantly higher than for the other years. As seen in the scatter plot, there are weak positive correlations between low birth weight and PM 2.5 levels, though some exceptions are in Hemphill, Wheeler, and Kennedy counties.
The R and R squared values demonstrate that the positive correlation between percent low birth weight and PM 2.5 levels is higher for New Jersey than for the other two states. This actually supported our literature review, as one of the articles we read focused specifically on the link between these factors in New York and New Jersey. There also seemed to be a delayed effect of air quality on low birth weight in Warren, Sussex, and Camden counties.
NDVI, or Normalized Difference Vegetation Index, is generally seen to increase in California. As seen on the scatter plot, there is a negative weak correlation between air quality and NDVI.
The low R and R squared values for NDVI in Texas are seen to stay relatively constant. However, when comparing air quality and NDVI maps over time, there seems to be a sort of delayed effect between the two. In other words, changes in PM 2.5 levels for 1 year seem to be correlated with NDVI for the next year. The PM 2.5 and NDVI for Fort Bend, Culberson, and Duval counties appear to have higher direct correlations.
There was no significant change in vegetation coverage over the 5-year period, so it is difficult to accurately analyze correlation between PM 2.5 values and NDVI in New Jersey. However, the R and R squared values indicate a negative but very weak correlation, and a more significant correlation in the counties of Hudson, Morris, and Passaic.
Across the board, we found little to no correlation between air quality and asthma, low birth weight, and vegetation, despite the already established correlations from previous research. This seems to contradict the strong correlations found during the process of literature review, indicating possible flaws or weaknesses in the available data.
Some explanations for this could be a lack of PM 2.5 sensors available for data collection in the areas that are particularly susceptible to the public health and vegetation factors studied. The former is especially true for Texas, as many of the counties had modeled air quality data, rather than actual data collected from monitors.
Another potential reason for the contradiction between reviewed literature and collected data is the imbalance of access to medical infrastructure that could prevent accurate counts of asthma hospitalization and birth weight. The demographic differences may also point towards an environmental injustice regarding the availability of air quality sensors in at-risk communities. For instance, we pulled some data from the real-time air quality monitoring network Purple Air, which sells sensors at a price range between $199 and $299. This indicates that education level and socioeconomic status may also propose an obstacle to air quality and health.
To conclude, the scatter plots exhibited correlations that were different from the literature that was reviewed, which could have resulted from sensor data, medical, and demographic limitations.
In the future, we hope to analyze the correlations in specific counties within our 3 states, as well as extend the research to a larger range of factors.
We also hope to investigate the distribution of air quality sensors and to help determine which areas within each state are in most need of more sensors.
The SEAS program has reinforced my interest in pursuing future research where I can use Earth observation data to help end environmental and public health disparities.
The NASA SEAS program has allowed me to expand my horizons and explore STEM in a new way. I've been able to meet so many like-minded people, and this experience conducting real research has inspired me to pursue it in the future as a career.
The NASA SEAS program has been an incredibly valuable opportunity for me to conduct research alongside driven people, which has led me to discover my passion for it. We would like to thank NASA, Texas Space Grant Consortium, Globe Mission Earth, Center for Space Research, the University of Texas at Austin, Dr. Pippin, Dr. C, Femi, Yitong, and of course our mentors, Sarah and Janine.
Thank you.
Great job for both teams. So we have several questions we'd like to ask all those participating in this two presentations to please turn on your videos and also unmute. So if Nihar, Ishan, Gardenia, Ali, and Audrey would please turn on their cameras and unmute. Our first question is for Ishan and Nihar. When your correlations came in and your data was not matching, how did you continue to work on your project?
I can talk about that. So when we first got the correlations not matching, we did kind of freak out because we were like, what are we supposed to do if we have no correlations? But then I thought of looking at it from a different angle. And Sarah and Dr. Pippin really helped us with this. They actually mentioned that there is this problem that they were looking at too of needing more EPA monitor data. And then while I was just thinking about that problem and then the correlations we didn't have, it struck me that we didn't have those correlations because we didn't have the data to get the correlations. And so then we just sort of shifted our focus to adjust towards that, and we're here where we are now. So yeah.
So Ishan, how would you propose implementing more air quality trackers in areas that need them, like Cancer Alley or in rural communities?
Sure, that's a great question. So Nahar and I have actually discussed like starting an activism program or something to actually get started and promote awareness about the issue. And in general, I think with more aware, because I think that air quality is an issue that a lot of people tend to skim over and don't realize that it's as important as it really is. So in general, we think that just generating awareness about the topic will naturally create more sensors and air quality trackers.
And for Gardenia, Audrey, and Ali, how do you explain the lag between the air quality and NDVI relationship? Are you unmuted? So we will go to Ishan and Nahar. What do you think could be done to make exposure to air pollution more equal to different populations in the US?
So that's sort of the issue that we're tackling, right? Is first of all, if you want to even get that issue resolved, you're going to need the proper data to get the proper, like, who even has unequal access? Like, we can't really answer that question right now without the data. So I guess the first step is getting the data. And then after that, say we do get the necessary data to get those correlations, I guess it's just raising awareness about who's getting unequal access through research studies like this that make those correlations. And then, you know, speaking at symposiums and conferences like this to get people start acting on those correlations and, you know, giving people equal access to things. So right now, it's basically mainly a data collection research thing.
So we're going to see if the sound is working for the girls, and if one of you could respond to the question, did you notice any differences in NDVI and air pollution among at-risk communities and versus urban areas? I know the sound was not working before.
So we weren't really comparing rural versus suburban areas like Nihar and Ishan. We were just looking at all three of our states on the county level, but that's definitely something we want to look into for future research, for like future steps in our project.
Okay, and one more question for the team. How do you explain the lag between air quality and NDVI relationship?
So since, I don't know if my microphone is working
Yes,
now.
it is working now.
Okay, good. So since NDVI is vegetation, and that includes things like trees, living things that are growing, we're going to see a delayed effect of that because air quality and pollution is something that affects like the growth process of these plants. So you wouldn't be able to see a very clear direct correlation between the same year. It would take a while for those air pollutants to actually affect the vegetation that's growing in the area.
Perfect. And if let's see, Allie maybe could answer, how did contradictions in existing research and your own research prompt you to analyze the accuracy of the available data?
So Allie actually couldn't join us today, but some of those contradictions are pointing us towards kind of the same conclusions that Ishan and Nihar's group are coming to. And that's just about like the spread of these EPH tracking sensors and whether or not they're actually measuring air quality in the areas that it needs to be measured, in the areas where these vulnerable communities are being impacted by air pollution and PM 2.5. So that is also something that we would like to consider and research more in the future.
Great. You've all done a wonderful job, and I've learned a lot from each of you. Thank you for your research. The aerospace engineering team designed a satellite to monitor global warming sources and solutions in Earth's upper atmosphere. The team chose environmental aspects to be monitored, defined the satellite orbit, selected sensors, determined the launch site, and chose the rocket to be used for launch. A special thanks to Dr. Wallace Fowler for his dedication and commitment to the SO2 team. Our first presentation is the GigaSat hardware and sensor team.
Hi, we're the hardware and sensor team of the GigaSat, and over the past 2 weeks, we've developed the inner workings of the satellite as well as its hardware and utility systems. My name is Adriana Gayton, and I'm a rising senior at the California Academy of Mathematics and Science in Carson, California.
Hi, I'm Bill Lamb. I'm a rising senior at Oakton High School in Vienna, Virginia.
Hi, my name is Neha Shukla, and I'm a rising senior at Cumberland Valley High School in Pennsylvania.
Hi, my name is Jude Asfel, and I'm a rising junior at Trinity High School, Euless, Texas.
Hi, I'm Sabit Kumar, and I'm a rising junior at Lake Travis High School in Austin, Texas.
We had mentorship and guidance from Professor Fowler.
Here's our outline that describes what we will be going over in this presentation. First, we'll be giving an overview of our project and mission, then transitioning into the AIRS and VIIRS instrument that will be utilized in our satellite. We'll then go more in depth to the 3 modules we've worked on, which are forest fire detection, emissions monitoring, and oil spills detection. Lastly, we'll talk about our future plans for SO2 detection, our satellite's utility systems, and end with the conclusion of our project and reflection of Cs.
In this section, we'll go through a project overview before diving into the details of the satellite. Introducing GigaSat. GigaSat, or the Giant Imaging Geostationary Atmospheric Satellite, is designed to monitor various environmental factors and prompt tangible action from wildlife officials, government authorities, and environmental scientists. It's located in geostationary orbit centered at 70 degrees west longitude to monitor regions in North and South America, along with Western Africa. The GigaSat project is possible with the support and guidance from the NASA SEAS internship program. This is an early visualization of the GigaSat's main body that we created on a computer-aided design program, including major components such as the sensor instrumentation, solar panels for power, body housing, station-keeping propulsion, thermal control, and communications antenna. The GigaSat includes 3 main modules or tasks within the satellite. Firstly, our satellite detects wildfires in remote areas using infrared technology to alert wildlife authorities to take action before the fire spreads. Secondly, the satellite monitors emissions from factories and coal-firing plants to make sure companies are abiding by their carbon promises. And lastly, the satellite detects oil spills and identifies key characteristics so that the oil can be removed to prevent further damage to the environment and to human health.
First, I'll be talking about the AIRS and VIIRS instruments that are used in both wildfire and emission detection. NASA's Atmospheric Infrared Sounder, or AIRS, was first launched in 2002 aboard their Aqua satellite. It is a passive instrument that gathers infrared energy emitted from Earth's surface and atmosphere globally, as well as collects data on important greenhouse gases emitted, generating new data each day. It consists of a cooled array grading spectrometer, cross-track, rotary scan mirror, along with a 4-colored imaging photometer and a multi-aperture spectrometer, among other components that work together to run AIRS. The next instrument we'll be using is VIIRS. NASA's Visible Infrared Imaging Radiometer Suite, or VIIRS, is a passive instrument used on SWOMI NPP satellite launched in 2011. It collects global satellite observation on land, ocean, and the atmosphere with sensors that span the visible and infrared wavelengths. VIIRS consists of a VIS-IR imager with day and night capabilities, as well as narrow band or hypospectral imagers, among other components that work together to run VIIRS. The first environmental factor we will be monitoring is wildfires. The FREYA module, which stands for Forest Fire Remote Environmental Yield Assembly, uses NASA's AIRS and VIIRS instruments in order to detect wildfires. The purpose of wildfire detection is to quickly detect brewing fires and provide information over monitored hotspots in specific areas in order to determine the severeness and whether the fire is beneficial or harmful. These forests are densely populated areas with an abundance of trees and wildlife, which can be severely harmed by the rapid growth of fires. So in order to protect and preserve these forests, as well as the animals and humans nearby, the satellite is meant to monitor the forests in order for the fires to be detected as soon as possible and is able to be quickly put out if determined that it will have a negative impact. Once the data from the monitored location is collected and a fire is detected, then the communication system will send down the information to the ground for wildfire authorities to determine the severity and the further call of action needed. A company called Frontier Wildfire Defense is an active wildfire tracker for the United States we could send down the monitored data to in order to provide the information to people through their app to have the least amount of casualties possible. AGU is also planning similar projects in this department with the same goals we could collaborate on. Now on how we'll be using the AIRS and VIIRS instrument. We'll be using the AIRS instrument in this scenario to provide a real-time infrared map of the spatial field of view pinpointing fires. The instrument can show a large field of view and has a moderately high resolution, which will be helpful in seeing a general overview of the geographic area of interest. AIRS is also able to track important gases found in wildfire smoke, like carbon monoxide, which will be helpful in detecting the fires early on. Once AIRS is able to give a general map of the spatial view, we will be using VIIRS in this scenario due to its large spectrum and its high resolution to give a more detailed map of the specific area the fire has been detected in, to give a more detailed idea of where the fire is and how severe it could possibly be.
The next module on the GigaSat will be dedicated to emissions detection. The goal of the GigaSat is to track environmental factors in geostationary orbit. One of the ways we plan doing this is with a module called PLEDGE, or the Plant Emissions Detection Geographer. This module would utilize the same AIRS and VIIRS instruments already aboard the GigaSat and potentially use London-based company Satellite Vu's infrared satellite technology for better resolution imagery. These instruments would detect greenhouse gas and heat anomalies throughout North America to monitor the integrity of corporations that have made carbon reduction promises. In a study done by New Climate Institute and Carbon Market Watch, 25 large multinational corporations such as Shell, Google, Volkswagen, etc. account for about 5% of global carbon emissions, or almost 2 billion metric tons of carbon a year. When faced with public pressure about their emissions, current research indicates that carbon reduction promises made by corporations on social media do not align with their actions. According to various studies, large corporations often mislead the public about the effectiveness of their greenhouse gas reduction plans, known as greenwashing, where they exaggerate or share false information about their efforts to reduce greenhouse gases. More data is also needed since NPR identified that while data is available from the International Energy Agency, this national data is not publicly available or is hidden behind costly paywalls, making it inaccessible for the public to hold companies accountable. GigaSat's pledge module would collect this data and make it publicly available, thus aiding independent research, which could help accelerate the global transition to low-carbon energy. Despite also making bold carbon reduction promises, the fossil fuel industry is, in actuality, cashing out on short-term profits over the well-being of our planet, expanding large-scale oil and gas projects that will produce greenhouse gases equivalent to decades of global CO2 emissions. Additionally, about a dozen of the largest oil companies are on track to spend $103 million a day for the rest of the decade to exploit new oil and gas fields, pushing the world past temperatures that leading climate experts say are necessary to avoid the most damaging effects of climate change. The AIRS, VIIRS, and satellite view instruments would collect daily greenhouse gas and infrared radiation information. GigaSat would collect this data and publish it on NASA's climate webpage in publicly accessible datasets, allowing regulators and those interested in a company's integrity to enforce climate promises made by the companies. Along with clear environmental benefits, the pledge module aboard the GigaSat has massive economic benefits. According to NPR, the White House predicted that climate change could reduce national GDP by as much as 10% in the coming century, with a cost of about $2 trillion yearly. Ensuring corporations abide by their carbon reduction promises would mean not only saving the environment, but also saving tens of trillions over the next few decades.
Let me introduce you to the next module on GigaSat, NJORD, or the Nautical Jettisoned Oil Recovery Detector. NJORD, fittingly named after the Norse god of the sea, will detect not only the presence, but the various characteristics of oil spills. This data will be sent to Earth, where it will mobilize cleanup crews to placate an oil disaster. But first, let's talk about oil spills themselves. The truth is that chemicals in oil spills can severely harm or even kill humans. And when hundreds of thousands of people drink from the same water sources where these oil spills occur, these health risks are legitimate. In addition, oil spills can harm wildlife in the affected area. Due to the adverse effects of oiling on animals, thousands of animals are killed every time an oil spill occurs. Lastly, an oil spill can devastate an economy. For example, the Deepwater Horizon oil spill cost the Gulf economy thousands of jobs and billions of dollars, the effects of which are still felt today. Currently, there is not a single satellite with an instrument dedicated to oil spill detection, so NJORD would provide a much-needed relief to this impending global crisis. NJORD will utilize 3 instruments, the first of which being the laser fluorosensor. The laser fluorosensor is the only active sensor on NJORD and will work by emitting UV radiation with an aimable laser and detecting the specific visible light returned by the oil due to its fluorescing capabilities. Because of the large power requirements of the laser, it will be outfitted with a capacitor to build up energy. This sensor will both pinpoint the location of an oil spill effectively and, as an added bonus, locate sunken oil, which is a dangerous phenomenon that occurs when turbulent currents shift oil underneath the surface of the water. The second instrument is a full-range spectrometer, which measures electromagnetic radiation all the way from ultraviolet to shortwave infrared. The sensor will detect reflected heat from the oil, which will allow us to measure the viscosity of the spill, crucial information to the ground crew. In addition, it will sense the reflected UV radiation from the sun of oil sheens, which are extremely thin and hard to spot layers of oil that occur during oil spills. Lastly, NJORD will employ a microwave radiometer. which will detect space-source microwave radiation as reflected by the sea. Using multiple wavelengths and calibration, we can determine the thickness of the spill, another piece of essential information if a cleanup is required. Overall, NJORD will revolutionize modern-day oil spill remote sensing and provide us with state-of-the-art methods of determining information about oil spills, creating new pathways to solving the constant threat of oil pollution.
In the future, our satellite plans to monitor sulfur dioxide in the atmosphere to measure the success and environmental side effects of future solar geoengineering methods. Global efforts to reduce rising temperatures has resulted in a new field, solar geoengineering. In 2018, researchers began experimenting with the idea of spraying sulfur dioxide, or SO2 particles, into the stratosphere as a method of rapidly cooling the Earth's surface temperature. SO2 sprays essentially reflect solar radiation back into space. The principle behind this method can be explained by natural phenomena, like volcanic eruptions. Mount Pinatubo's eruption in 1991 sprayed over 20 million tons of SO2 into the stratosphere, creating a haze of SO2 particles that reduced Earth's temperature to what it was hundreds of years ago. It's an intermediate solution to reduce temperatures in the short term in order to reduce heat-related deaths and environmental damage, especially at the equator. A group of Harvard postgraduates formed a team in 2019 known as the Stratospheric Controlled Perturbation Experiment, or SCOPEX, to test solar geoengineering in the field for the first time. Backed by the Gates Foundation and with a $3 million test trial, the group planned to send 2 steerable balloons to the stratosphere to simulate large-scale SO2 injection using calcium carbonate. However, this solution isn't perfect, and there are concerns and intense debate from several environmental groups on the downstream effects of SO2 injection and possible harms of blocking out sunlight, especially on equatorial regions, such as causing lower crop yields and changing rainfall patterns. Because of pending discussions with indigenous groups at the launch site in Sweden, the project is currently paused to prioritize environmental concerns and ensure these projects are built responsibly and with long-term considerations. With future projects exploring solar geoengineering further and the possibility of large-scale SO2 injection increasing, a future goal of the GigaSat includes monitoring the progress and success of stratospheric SO2 injection from a geostationary orbit in our field of view. The GigaSat instrument suite already includes channels to monitor SO2 absorption within our AIRS module, so our team is equipped to include SO2 monitoring as part of the data streams sent back to Earth, if these advancements demonstrate need to have significant atmospheric monitoring.
For a communication system, we will be using an S-band radio wave transponder that has a frequency of around 3 gigahertz in order to communicate the collected data back to Earth. The reason why we are using a low frequency band is because we want to conserve power rather than other higher frequency bands like Ka and Ku bands, which use much more. Additionally, an S-band is more specific in who it gives its information to, instead of to the general public like higher frequencies do. The GigaSat will contain 10 meters squared of 6 millimeter thick solar paneling to supply its power needs. This provides 1.5 kilowatts, more than our system requires. In total, the sensor requires 1,390 watts of power. We overcompensated the power as a buffer because of solar panel degradation over time, which is 0.5% per year, due to things like thermal cycling and ultraviolet exposure. This gives us a 95% efficiency in 10 years fulfilling our power needs.
For station keeping, GigaSat will utilize instruments to account for attitude and drift control. 4 reaction wheels, each with a mass of 10 kilograms and speeds up to 6,000 RPM, will aim the satellite, with 1 wheel per rotational axis plus 1 spare. These wheels can be spun at variable speeds using electric motors to orientate the satellite and prevent tumbling. To slow down the wheels, reaction control system thrusters are fired to cancel the force resulting from slowing down the wheels, a process called angular momentum desaturation. Our orbit team, which will present next, determined that the GigaSat will drift 2 meters a second a year. To prevent this, NASA's current NSTAR iron thruster would be used. Using the rocket equation with a given specific impulse of 3,100 seconds, an expected service life of 10 years, and a dry mass of 816 kilograms, the amount of xenon fuel needed for drift control would amount to less than 2 kilograms.
For the instruments to function, it is extremely important that the satellite has optimal temperature. Our GigaSat will be comprised of heat pipes and radiators in order to regulate the temperature. Heat pipes will be used as they are one of the most efficient ways to move thermal energy from one area to another, while radiators will be used in order to eject any excess heat from our satellite as it is expected to experience major fluctuations in temperature when in space. Gold multi-layer foil insulation will be used to act as a blanket to maintain heat. Without the gold foil, heat will easily escape from our satellite into space. To summarize, the GigaSat will utilize AIRS and VIIRS instruments to execute infrared monitoring, monitor 3 environmental factors, and make use of several satellite utility systems. My SEAS experience has inspired me to work even harder and allowed me to realize that it is possible for me to achieve my dream of becoming an aerospace engineer. I am incredibly grateful for being given an opportunity to work with a team full of amazing and like-minded students.
SEAS has inspired me to continue my passion towards aerospace engineering. From this program, I have made friends with people all around the country, and I'm so lucky to have gotten the opportunity to gain hands-on experience.
Being a part of SEAS has opened new doors of opportunity for me in the aerospace field. I'm so grateful to the SEAS program for providing me with real-world experience and the ability to conduct high-level research in fields that are exciting to me. I'm beyond grateful to Professor Wallace Fowler for his continued support and guidance throughout the way. He made this process so fun, and his experiences and stories guided us through every step of the project. Being in the SEAS program helped me discover my passion for aerospace engineering, and I'm excited to take it further and use this experience to create a positive impact on my community through engineering.
Being a part of SEAS has opened my eyes to all the possibilities and opportunities I have for my future. It has motivated me to work harder in order to achieve my dreams of becoming an engineer. I am also thankful for the team I have worked with. I could not have asked for a better group of people.
SEAS has taught me how to work as a team and carry out the engineering process. Most importantly, SEAS introduced me to some amazing people who I will forever remember as mentors, colleagues, and friends. We would like to thank NASA, SEAS, and the Texas Space Grant Consortium for providing us with the opportunity of exploring our passions and furthering our interests in the field. We would also like to thank the University of Texas and Center for Space Research for providing their facilities throughout the duration of our internship.
A special thanks is due to the NASA SEAS administration, staff, speakers, mentors, and peers in their immense help throughout this process. Finally, we'd like to thank Professor Wallace Fowler for his guidance and support. We couldn't have done it without you.
So we invite the team to please turn on their cameras and unmute. We have several questions. The first one is for Neha. Isn't the SO2 injection only a temporary fix for cooling the Earth?
Thank you so much for that question. And I definitely agree. A lot of research has been showing that, SO2 injection is really a short-term fix and more of an intermediate solution so that we can kind of buy ourselves a little bit more time before we're able to tackle, larger issues like climate change, carbon emissions, and so on. So a lot of research has also showed that there can be negative side effects of SO2 injection. And that's why a lot of field testing is being done currently to see, what are these side effects in terms of air quality, in terms of, other, indirect effects on the climate, such as changing rainfall patterns, affecting crop growth, and et cetera. So I think our satellite doesn't really aim to conduct SO2 injection. In fact, our satellite actually plans to do the opposite. So in the future, as companies begin conducting SO2 injection more, and if we see that this becomes a viable field, our satellite already contains modules within the AIRS module and channels to actually monitor SO2 absorption. So we'll be able to see, are there negative side effects of this technology, and what areas is it affecting? So, our satellite is more planning on in the future monitoring the positive and negative side effects rather than actually conducting SO2 injection.
Great. The next question is for anyone on the team. If you could pick one additional module to include on your GigaSat, what would it monitor?
I guess I'll take this one. One of the big things that we were actually looking into at the beginning was actually measuring wind patterns with a scatterometer. It was an idea that didn't really work out because of the orbit that we were in. But we were originally looking at like hurricane tracking and other sort of wind patterns. So if we could figure out how to track winds within a geostationary orbit that we're in right now, that would be another great module that we would like to add to our satellite.
Great. And the next question is for Bill. What are some strategies to keep companies accountable to reduce their environmental footprint?
Great question. So for the GigaSat, it's mostly just to like monitor emissions activity and provide data for regulators and those in the public that are interested in a company's carbon emissions. But a good way is to call them out and to talk with your local policymakers, and to ensure that when a company makes a statement about their carbon emissions reduction plans, that there are people and legislature that are able to check on their word to see if they're actually emitting or reducing emissions as much as they say. But these regulators need data to back up their research. And so that's where the GigaSat comes in. It would monitor the amount of emissions that any one company has, whether that's from vehicles or energy production, and then give that data to regulators or the public to then conduct their own research and check on the behavior of these companies.
So if we could have one of the other teammates answer, what do you hope to do with the data that you collect from GigaSat if it were to come to fruition and you were able to launch?
We actually have a really wide target audience for the data in the GigaSat. So I think Renee mentioned the forest fire module, Freya. So for that module, we would be immediately alerting wildlife officials, government authorities in that area and fire departments so that people can immediately be mobilized in terms of reducing the spread of forest fires. Then Satvik talked about NJORD, which is the oil spill detection module. I think in that module, it would be really great to alert, again, local government authorities, oil spill cleanup crews, and just people who are able to, again, be mobilized to reduce the spread of oil spills in that issue. And then for the third one, which is emissions detection, again, this would be more so for regulators, climate scientists, and also the general public to make sure that, as Bill said, keep companies accountable for their carbon emissions. So that's kind of, we have a pretty broad and wide target audience, but for those different modules, that's who we'll be sending the data to.
And the last question for the team is, how do oil spills affect the animals? And what happens if the oil spills are left untreated?
Oh yeah, so that was my primary area of research, oil spills. I think one of the big things that you got to consider is animals maintain a state of homeostasis, which is essentially keeping their bodily equilibrium throughout different systems. And essentially what oil does is it disrupts those systems. So within animals specifically, you might have otters with insulation, with fur insulation, and oil disrupts that system, and then they're not able to survive in the cold ocean anymore. It could be pelicans, their feathers' ability to be water resistant. That's another thing that oil is going to disrupt. So it really could be, pelicans can't fly, otters can't swim, turtles can't breathe, just any sort of animal could be affected by oil spills.
Great. Well, you have all done an amazing job. We appreciate your dedication and your research. We're going to move on to the GigaSat orbital team and their presentation.
Hello, we are the GigaSat orbital team, and we are going to describe the orbital mechanics behind the hardware team's satellite. Hello, I am Colby Drabick. I'm a rising senior at Deering High School in Portland, Maine, and I intend to either be a chemical or aerospace engineer.
Hi, I'm Hannah Singer. I'm a rising senior from Ursuline Academy of Dallas, and I hope to become an engineer one day.
Hi, I'm Caitlin Watt, and I am a rising junior at Trinity Classical Academy in Valencia, California, and I aspire to be an aerospace engineer.
Hello, my name is Samuel Cater. I'm a rising senior, and I attend Broward College in South Florida. I intend to be an aerospace engineer in the future.
Hello, I'm Sophia Gell, and I'm a rising senior at Scotch Plains Famine High School in Scotch Plains, New Jersey. I hope to pursue a career in aerospace engineering in the future.
When we set out on this mission, we aim to support the hardware team in their mission by crunching the numbers and figuring out how to efficiently get from low Earth orbit to geostationary orbit, an orbit that allows us to monitor one position of the Earth at all times. We did this by ensuring we met these 5 mission objectives. The first, delivery and positioning. And for delivery and positioning, we need to make sure that the payload makes its way from low Earth orbit to geostationary orbit, fulfilling the requirement to see one part of the Earth at all times. The next was orbital insertion. We need to calculate the engine burns needed to get us from low Earth orbit to geostationary orbit and make sure those were accurate and efficient. The next thing we need to do was we need to set up safe disposal and station keeping procedures. To ensure that the assets of us and others are protected in the dense region of geostationary orbit, we need to ensure that every move we make does not endanger our satellite or other companies' satellites, and we need to ensure that we act in a responsible manner in all maneuvers. We also need to meet the mission criteria to ensure that the satellite is in a position to collect and monitor crucial data from crucial areas and to satisfy the hardware team's operational requirements. Lastly, we need to ensure the longevity of the satellite. To ensure that our satellite works for a long time in the orbit we intend it to work in, we need to position it very accurately, so we cut down on the need of station keeping as much as we can, prolonging its lifetime. Here's our mission overview. We start in a build process and we eventually make our way to launch. From launch, we will launch into low Earth orbit. We'll perform what is called a Hohmann transfer, and people will explain this later. We perform that Hohmann transfer into geostationary orbit. We circularize the geostationary orbit. We commence observation. After about 10 to 20 years, we go from observation to end-of-life procedures, and we move our satellite into the geograveyard. And as I said, people will explain these more in depth coming up. When we were looking at launchers to get our satellite into orbit, we considered multiple ones, including some foreign options such as the Ariane 5. We eventually settled upon the domestic Falcon 9 provided by Space Exploration Technologies, or SpaceX. They're an American company who launches out of Cape Canaveral in Florida, providing us an inclination of 28.5, easing the amount of plane change we need to do to get to our geostationary orbit. We chose the Falcon 9 for a variety of reasons. The Falcon 9 offers us the lowest cost to orbit and has one of the highest reliability streaks of any rocket. The only thing that can rival the Falcon 9 in terms of reliability is possibly the Russian Soyuz. With this elimination of a lot of risk, we can lower our insurance costs and have less worry when we choose to launch our satellite. The next reason is it has a low inclination at its launch. Falcon 9 launches from Cape Canaveral, and as I've said, that gives us a 28.5 degree inclination when we launch due east, allowing us to save some fuel during our plane changes compared to other options. Lastly, Falcon 9 offers an amazing cadence. They offer us the quickest boardroom to orbit time, allowing us to go directly from the build site to the launch site, as SpaceX launches at a rate of about 1 launch per every 10.1 days. Lastly, I want to talk about the launch site. We're launching from Launch Complex 39A, SpaceX's modern launch site, allowing easy access to our orbit. SpaceX is an industry leader, and they offer horizontal stacking and rollout, as well as support by our partners such as NASA and the United States Space Force to increase the synergy between the many operators of this mission.
This is the diagram of an elliptical orbit and the orbital elements that define its shape, its orientation, and the satellite's position in orbit. The apogee is the location in orbit where the spacecraft is the farthest away from the central body with the slowest velocity, while the perigee is the closest with the fastest velocity. The ascending node is the point in orbit which crosses the equator from south to north, while the descending node crosses from north to south. Similarly, the right ascension of the ascending node is the angle starting from the vernal equinox to the ascending node of the orbital plane. The argument of perigee is the angle from the ascending node to the point of perigee, while true anomaly is the direct location of the satellite in orbit measuring from the perigee. Inclination is the angle between the equatorial plane and the orbital plane, which determines the tilt of the spacecraft's orbit. Our satellite in specific is in a prograde orbit moving from east to west with an inclination of less than 90 degrees. However, GigaSat will not be in an elliptical orbit because, since it is in geostationary orbit, it will have an eccentricity of nearly 0, where this determines the shape of the orbit, making it more circular.
After the spacecraft is launched, it is placed into a low Earth orbit, which we call a LEO, and can also be called a parking orbit. A LEO is a nearly circular orbit. GigaSat's altitude is roughly 265 kilometers above the Earth's surface, and it has a period of 90 minutes. The semi-major axis, or the radius, of GigaSat's LEO is 6,643 kilometers, as shown by the yellow line. While in this orbit, the satellite will move at a constant velocity of 7.746 kilometers per second. Additionally, we will place the satellite at 70 degrees west. This translates to 290 degrees east. In the image, 70 degrees west is the pink dot near Ecuador and Colombia, and the satellite's field of view is the yellow round. With this field of view, the GigaSat can monitor wildfires, oil spills, and more. This is the LEO ground track. A ground track is the path on the surface of the Earth directly below the spacecraft. It is a set of points at which the satellite will pass overhead. The Earth rotates at 15 degrees per hour, so every 90-minute orbit, the Earth rotates 22.5 degrees underneath the spacecraft. If you look at the graph, one node to the next node, or one equator crossing to the next, is 22.5 degrees and is equal to one 90-minute period. This ground track shows the satellite's first 5 orbits. The purple dot is the first descending node at 5 degrees. This is the first time the satellite crosses the equator after launch. A descending node is when a spacecraft crosses the equator going north to south. And if you look at the graph from left to right, you can see that it descends as it crosses the equator. Additionally, the Earth has a non-spherical shape, and it bulges at the equator. And it is this bulging that causes the line to move slightly to the west with each subsequent orbit. GigaSat's mission cannot be conducted from LEO, however. The satellite needs to be transferred to its geostationary orbit. So we use a Hohmann transfer, which is an elliptical transfer orbit used to maneuver the satellite from LEO to its geostationary orbit, GEO. A Hohmann transfer consists of 2 burns, one to get the spacecraft out of LEO and one to get the spacecraft into GEO. A burn is the turning on of a rocket or the burning of propellant to change the velocity of the spacecraft assembly so that it can escape its current orbit and maneuver into another one. After the first burn, the satellite will coast uphill in an elliptical orbit, which is shown in red in the moving image and green in the hand-drawn image. The spacecraft will only travel on one half of the elliptical orbit, 180 degrees. This is the same LEO ground track, but this one highlights the last 2 to 3 orbits before the first burn of the Hohmann transfer. If you look at that small line on the far left, imagine that it stretches to the equator. That crossing of the equator is an ascending node and is roughly the location that initiates the Hohmann transfer, 189 degrees east. Where did that 189-degree longitude come from? Well, the Hohmann transfer spans about 100 degrees from burn 1 to burn 2. We want burn 2 to occur at the target longitude of 290 degrees east, so the first burn needs to be 101 degrees west of that, which is 189.
The first burn will start off our journey from LEO to GEO. We can recall that a burn refers to the event of turning on a rocket to change the velocity of the spacecraft assembly. At burn 1, it is at stage 2 of Falcon 9. After about 21 hours, the GigaSat will make 15 revolutions around the Earth, and the satellite will thrust as it crosses the equator. This chart gives the ascending nodes and descending nodes as well as the NET at each revolution. An ascending node is when the spacecraft crosses the equator on the way from south to north, and a descending node is when the spacecraft crosses the equator on the way from north to south. The NET is the time from the first node starting from 0 to about 22.5 hours. The spacecraft first crosses the equator at a descending node of 5 degrees, and at this point, the satellite will begin its first burn at the ascending node, which has a longitude of 189 degrees. The GigaSat ends its 15th revolution and fires the rocket with this longitude. With an inclination of 28.5 degrees, the GigaSat will start its transfer orbit to reach GEO orbit. The transfer orbit takes about 5 hours and 16 minutes. During this stage, the rocket attached to the satellite will be dropped and will go back down and burn up in the atmosphere. This is called a retrograde burn. A retrograde burn is one that subtracts from the ship's orbital speed. We don't want to have to accelerate all that extra mass. Since the speed of LEO orbit is around 7.75 kilometers per second, GigaSat will thrust up to a speed of 10.2 kilometers per second, coast uphill, and enter an elliptical orbit at the perigee. Therefore, the delta V is 2.46 kilometers per second. The satellite will travel 180 degrees and reach the apogee, where it will then make the second burn. These ground tracks show the transfer orbit. The left end of the data shows the first burn at 189 degrees. As the satellite starts its elliptical orbit, we can follow the tracks at a constant speed, since the satellite is traveling faster than the Earth. The Earth turns underneath the satellite at a constant speed, but the satellite slows down as it coasts uphill from 180 degrees as we go from perigee to apogee. Because the spacecraft has a slow velocity, the Earth's constant speed moves faster than it, and the spacecraft backtracks relative to the Earth. Therefore, on the ground tracks, the GigaSat traveled 180 degrees, yet at the far right point at the end of the data, it backtracks 71 degrees. So the satellite really only traveled 109 degrees on the graph from point to point. Geo altitude, again as we cross the equator, GigaSat executes its second thrust to enter GEO. Burn 2 will occur at the apogee, and at this point, the satellite will be traveling at speeds of 1.6 kilometers per second. When the second thrust is made, the spacecraft will travel at speeds of 3.07 kilometers per second in order to stay in GEO orbit. The delta V is 1.8 kilometers per second. It is important to note that each of our 2 thrust events include a part of the required 28.5 degree plane change maneuver. This means that these thrusts are not in the plane of the current orbit. In GEO, over our target longitude, we orbit in GEO for the satellite useful lifetime of about 10 years.
This is a diagram of the equatorial plane, labeled in green, and the orbital plane, labeled in red. This is the second burn, where there is a 26.3 degree plane change in order to relocate to the equatorial plane, where the geostationary orbit will be. VC2, which is 3.07 kilometers per second, represents the circular velocity of the satellite on the orbital plane, and VT2, which is 1.6 kilometers per second, represents the transfer velocity to the equatorial plane. Using the law of cosines, we found the rate of change in velocity between the 2 vectors, which was 1.78 kilometers per second, allowing us to understand how fast the transition between both planes is. After this, the satellite will be in geostationary orbit, where it will be capable of performing its functions properly in the most efficient location. However, once securely in orbit, that does not mean that the work is over. Since the Earth is not a perfect sphere, as the north and south poles are flatter due to its rotation, the orbit is not completely steady, as the satellite may begin to drift to the west. For this satellite in geostationary orbit, the drift rate will be around 2 meters per second per year, which is the delta V. Delta V is the change in velocity, otherwise known as acceleration. Though there is no atmospheric drag, since a geostationary orbit is too far away from Earth in comparison to a low Earth orbit, solar winds, which are streams of particles released from the sun, collide with the satellite and impact its position and function. In order to correct this, thrust is needed to put GigaSat back into its correct location in orbit.
300 kilometers higher than that of a geostationary orbit. Geograveyard orbits are used to reduce the amount of space debris found in Earth orbit, which reduces the chances of collisions in Earth orbit. Geograveyard is used in accordance with regulations set by the Interagency Space Debris Constellation Committee. Geograveyard could prove to be a vital resource once we find a way to access the equipment on the decommissioned satellites. GigaSat has a planned lifetime of about 10 years. Once these 10 years have passed, GigaSat will be transferred from a geostationary orbit to a geograveyard orbit to comply with space laws. GigaSat will be relocated using a Hohmann transfer. We will initiate the transfer once the overall mass of GigaSat reaches 820 kilograms. The transfer will use 2 burns that will use 2 separate solid rocket boosters located on opposing sides of the GigaSat. The 2 burns surpass the minimum delta V of 11 meters a second required to transfer to GeoGraveyard. After the transfer, the GigaSat will be decommissioned indefinitely or until we find a way to retrieve the equipment aboard the satellite. So, in conclusion, we'll be launching GigaSat from Cape Canaveral aboard the Falcon 9 rocket. GigaSat will enter low Earth orbit, and after approximately 22 hours, it will be transferred to a geostationary orbit over 70 West using Hohmann transfer, including a plane change. GigaSat commences monitoring of vital environmental factors for a period of 10 years before being decommissioned and transferred to GeoGraveyard. However, we wouldn't have been able to complete this project without everyone at SEAS, which brings us to the conclusion of our...
We would now like to take some time to talk about what SEAS has meant to us. For me, SEAS has meant a lot to me. SEAS has allowed me to further my collaboration skills as I worked with a team to design the concept of a satellite, something I thought I would never do. SEAS has also allowed me to further focus what my career path is going to be. Furthermore, I have also made connections with people who have the same interests as me, and I hope these connections grow into lifelong friendships. Lastly, SEAS has allowed me to gain further experience in a high workload environment and study under an experienced professional.
I appreciate SEAS because it allowed me to explore working in a team further, as well as developing my teamwork and time management skills. SEAS also allowed me to develop connections with like-minded individuals who shared my passion for STEM and aerospace engineering.
SEAS has helped me step out of my comfort zone back at home and immerse myself in new STEM experiences. I met many new people who share my interests, and I learned of new paths to take to achieve my future goals and then some. I thank C's for allowing me to, for the first time, work on a realistic and creative project that helped build upon my knowledge of aerospace engineering.
I am so thankful that I had the opportunity to be a C's intern. What I have learned and the relationships I have built truly make this program special. I have met the most wonderful and hardworking staff, mentors, and peers here, and I will never forget the memories I have made with my team. C's only furthered my interest in aerospace engineering and gave me a taste of what I could accomplish if I worked hard towards my dreams.
These, I was able to apply my knowledge to something greater than myself in an uplifting environment where I was encouraged to make mistakes and try again. C solidified my hope to become an engineer one day, and I am grateful for the people I met and the experience I gained during my time here. As a whole, we would like to thank CES, NASA, and the Texas Space Grant Consortium for inspiring us to further our career in education and expand our connections in the STEM field. We would also like to thank the University of Texas and the Center for Space Research for providing their facilities, knowledge, and encouragement through the duration of our internships. And finally, on behalf of the entire SO2 team, we would like to thank Dr. Fowler, our mentor, for everything he did for us. We admire his passion and dedication to both STEM and our project, and we could not have done this without him. So thank you, Dr. Fowler, for guiding us through our project, imparting us with your wisdom, and furthering our education in the STEM field. These are all of our citations, and thank you for attending our presentation.
So we have several questions for the orbital team. So we invite you to turn on your cameras and unmute. The first question is, what software did the orbital team use to determine these calculations?
I can take this one. So we used a software called TK Solver, which basically allowed us to input the math problems that were relevant and then solve it for multiple different variables, which allowed us to get the optimal answers to the equations that we needed. So TK Solver is the software that we used.
Great. And why did you decide to have 2 burns opposed to 1 or more than 2?
I can take that one. So the GigaSat needs 2 burns because it is going from one orbit to another. It needs 1 burn to get itself out of the low Earth orbit. However, it can't just float into its geostationary orbit. It needs a second one to solidify its placement in that orbit. So it needs 1 to get out of LEO and 1 to get into GEO. That's why it has 2.
And does the geostationary position of your satellite limit its range of observation? And if so, how many of these satellites would you need to monitor the world?
Yes, it does limit. So each satellite has, when it's in geostationary, it has its own field of view. So if we wanted to monitor the entire Earth, we would need 3 satellites all 120 degrees apart to get each third of the Earth.
Next question for someone on the team. How will your research affect the Mongolian throat people, like they are located in the epicenter of the launch site?
I think it will benefit them. You know, everyone's affected by climate change, including the Mongolian throat people. So I imagine it will be very beneficial for them in the long run.
So did the CES Module 2 training on orbits provide a satisfactory basis for your project? Could that training be improved, or was it useful in your research?
Yeah, I can take that one. So when we were in this program in the run up to coming in person, we had to do some modules that trained us in what we were doing. One of them was orbital mechanics. That one, module 2, was orbital mechanics. I think it offered a very good basis for what we needed and a very good basis for what everyone on the program needed. As we were an orbital team, we needed a little bit more, but we got a very solid basis from that, and it brought you up to speed. So everyone, when we got down there, knew what they were talking about.
Great. And so the next question is, why does the satellite need to be in LEO first?
I can take this one. So basically, we're going to be doing a Hohmann transfer. So first, it has to go, when launching from Kennedy Space Center, it goes up to LEO, which is the closest orbit like to Earth. And then after that, we have to do a 180-degree transfer to GEO. So we can't just go straight to GEO because you have to maintain like a steady orbit first, and then you transfer up from there.
So the next question is, what is a ground track and how do you determine it?
So a ground track is the satellite's paths traced on the Earth, and we determined it through the TK Solver software. We just plugged all the formulas and the numbers in, and it chucked out our ground track. I think the most important part was not creating the ground track, but interpreting it. So the most important part of our ground track for us was the ascending and descending nodes, because those showed us how many orbits Gigasat had made. And with that information, we could initiate a Hohmann transfer and get it into its geostationary orbit for observation.
And then the last question for the team is, Kennedy Space Center the only launch option, or why did you choose to launch from Kennedy Space Center?
Yeah, I can take this one. We chose Kennedy Space Center for two reasons. One of them is that SpaceX only offers two launch sites, one in Vandenberg, California, and the other one in Kennedy Space Center. And the Vandenberg launch site really only serves polar orbits, so orbits that go over both poles. While the Kennedy one serves more ones that go over the equator. And as we wanted our satellite to be as close to the equator as possible, seeing as that what geostationary orbit is, we chose to launch from Kennedy Space Center. And I think we chose Kennedy Space Center also because it is SpaceX's more inclusive platform where they have every bit of infrastructure that we would need.
Terrific. Well, you have all done a wonderful job. I appreciate your research and your willingness to answer all of the questions about the project that you worked on. So thank you. So we're going to take about a 20-minute break. We invite you to watch the highlights of student accomplishments during the Earth and Space Science course. Many of the students had to produce materials, and we would like to give a special thank you to Teresa Howard and Asha Karmaker for scoring and preparing these highlights. We would like for you to join us again at 2:30 when we come back to begin our next series of presentations. So enjoy the Science Symposium Climate Science background. What great work from all of our interns, and special thanks to Teresa Howard and Asha for putting that slideshow together. So welcome back to the SEAS 2022 Science Symposium. Our first technology project is the Roads on Icy Worlds team. This team tackled a mission to Europa following NASA's upcoming Europa Clipper mission. Teams face challenges in engineering and programming, analysis of biological signatures and geologic features, while building and programming robots and drones. A special thank you to their project mentor, Angelita Crenshaw. So welcome to the Roads on Icy World team.
Good afternoon. We are the Roads on Icy Worlds team, and today we are discussing our research about our rover mission to Jupiter's moon, Europa. For decades, people both within and outside the science community have dreamed about humans discovering life beyond Earth. That dream may be accomplished by investigating Europa's cold and icy environment. NASA scientists theorize that the interior ocean of Europa could sustain life. Our research was divided into two main aspects. First, we completed the Roads on Icy Worlds Engineering Challenge, which simulated a rover mission that incorporated robotics, programming, and sample collection. Then, we expanded the scope of our project by conceptualizing a realistic Europa rover using 3D modeling. Now we will introduce ourselves.
Hi, I'm Alan Dechman. I'm a rising senior from Miami, Florida, and aspire to become an electrical engineer in the near future.
Hi, my name is Michelle Fang. I'm a rising junior in Allen, Texas, and I have an interest in math.
Hi, I'm Tamara Kasakovic, and I'm a rising senior from Old Bridge, New Jersey. I aspire to become a software engineer in the future.
Hi, I'm Hope Eaton. I'm a rising senior from the island of Kauai in Hawaii. I'm interested in pursuing mechanical engineering.
Hi, I'm Kayla Regal, a rising junior from Greenbelt, Maryland, and I hope to become an experimental particle physicist.
Hi, I'm Ava Sadasavan. I am a rising junior from Austin, Texas, and I aspire to pursue computer science and electrical engineering.
My name is Ana Sanchez, and I'm a rising senior from Far, Texas, and I hope to someday become a mechatronics engineer.
Hi, I'm Carmo Costo. I'm a rising senior from Philadelphia, Pennsylvania, and I would like to become an aerospace engineer.
This is the mission patch we designed to represent our project. The mission patch displays our rover on Europa wearing ice skates to indicate Europa's icy surface. In the background is spelled Roads as a constellation, which is the name of the robotics challenge we undertook. Then underneath that is our team name, Ice Vikings, which is illustrated by the Viking helmet on our rover. Lastly, we created the mission patch in the shape of an octagon because we have 8 team members.
Now we will move on to the background of our mission. Europa is a moon orbiting Jupiter, dubbed a Galilean moon due to it and 3 other moons being discovered by Galileo. Europa has a subsurface ocean hidden underneath a water ice crust and heated by the mantle underneath.
A few of the challenges of a rover exploring Europa include the unpredictable terrain, low temperatures, and distance away from the Earth. Europa's oceans are above a hot rock layer, causing the heating of the oceans and the shifting of the icy surface. Europa's chaos region is very rugged and has many cracks and obstacles that the rover will need to maneuver. Due to Europa's long distance from the sun, the temperatures there are very low and the communication with Earth's mission team would be very delayed. So the rover would need to protect itself from the cold using insulation and have autonomous features.
But why should we travel to Europa? Scientists believe there is a good possibility that some form of life lives on Europa. Some evidence for this is the ocean underneath, which has been detected through plumes of water rising from Europa. And due to tidal forces, the ocean is heated, keeping it liquid and allowing for proper conditions for life to form.
Another reason for Europa's possibility of life is the magnetosphere. Jupiter's magnetic field is being disrupted by Europa, and scientists infer that it is because of an electrically conductive fluid, specifically salt water, under Europa's ice layer.
Also, Europa's extreme conditions are suitable for some microbes that live on Earth, so life on this moon is realistic. One of the future missions to Europa is NASA's Europa Clipper, which is set to launch in 2024 and will send an orbiter spacecraft to determine if Europa is suitable for life. Another future mission is ESA's Jupiter Icy Moons Explorer, which is set to launch in 2023 and will make detailed observations about Jupiter's system and its 3 largest moons.
Next is the engineering component of our project, the Robotics Challenge Roads on Icy Worlds. Our project objectives were to keep a mission development log that we updated every day with our progress, to design, build, and test the samples, rover, and drone, build the Europa map, and construct barriers, and program the rover to complete the challenges autonomously. The objectives of the map were to first choose a landing site that we would deliver the lander to with the drone. After the drone completes its part, the rover autonomously collects the samples from the sites and returns them to the starting point.
Our team members calculated the important points and lengths needed to map out features such as barriers, landing targets, the point of interest, and sample sites. Our work included math applications like law signs, slopes, and area formulas.
We made the field map by putting together white poster boards. The total area of the map is 8 feet by 5 feet, and we left some excess to label the measures. This would make it easier for us when plotting the points for our barriers and sample sites. We built actual physical barriers to simulate obstacles. We also have this blue spot on the map that the rover is supposed to detect with the color sensor. So now the drone and the lander. We've tried multiple designs for the lander. Our goal was to create a loop on the lander that the drone would be able to hook onto. And then upon release, the lander would hit the ground and the drone would detach. We tested different weights for the lander to see which would fit the best with the drone. We figured it couldn't carry more than 30 grams. So our final design only weighed 27 grams. We had 2 drones in our possession, and we found that the smallest one was the most accurate to fly with. And that's the picture on the right. To carry the lander, we used a string first and taped it to the drone. But then the string would swing too much. So we decided to use a copper wire instead for stability, and we taped it to the drone. After adding all those elements, we were able to fly the drone safely. The drone would take off separate from the lander, then it would pick it up, carry the lander to the landing spot on the map, and drop it right on the target. And this is the video of our drone carrying the lander to the map.
We built our rover using the Spike Lego kit. None of us had ever worked with Spike before, so it was a challenge to learn how to use it and its new technology. But we were able to overcome this by following online tutorials, researching errors as we went along, and continuing through the engineering process through the building stages of the rover.
Once we had a better understanding of how to work with our material, it was time to conceptualize what our working rover would look like. We had a group meeting and decided on the following. The rover uses a 2-pronged lifting mechanism to collect 2 samples at a time, 1 on each arm. It has large wheels with strong tread, best suited for traversing Europa's icy surface. Lastly, it has a color sensor for the rover to identify potentially interesting samples. Specifically, because Europa is an icy moon, anything on the surface that is not white may contain minerals and should be investigated.
Version 1 of the rover development process. On the left is the Spike rover design we used to help build our own. However, we made some slight modifications in order to adapt it to our map project. Our biggest challenge with this was understanding completely how our model rover worked before moving on to make the modifications. We ended up flipping a few pieces and adding others for stability in order to get a 2-pronged lifting mechanism shown in the red.
Once we finished designing our rover, we started programming it. And just like any mission, we faced challenges, and we quickly realized that some changes needed to be done. The first challenges was the wheels. We used the wheels with no tread found in the spike kit, but the movement of those wheels were not predictable enough. So we decided to use some other wheels found on an EV3 kit used in previous years that had the treads on it, and that fixed the first problem. Then the second problem was that even after we got the coding done, we were not able to be very precise with the alignment each time we tested it, and this messed up our measurements, so the rover's path would change slightly every time. We fixed this by marking some points and lines on the map to make sure that the samples and the rover were always aligned the same. Also, slowing down the rover speed and adding lots of pauses helped with precision. The last challenge was that the rover was unbalanced due to the weight on the front. To fix that, we replaced the ball at the front of the rover with a heavier one, and then the robot was balanced. We were then able to run our code fully, and after multiple tries, it finally worked.
Here's what the changes to the wheels, the ball look like, as well as the color sensor that we added.
And here is our final rover design.
Along with 2 planned orbiter missions, a Europa lander concept has been proposed, but it's not currently set to be built. Rather than a lander, we propose a rover that would have optimal mobility for ascertaining a diverse set of samples for analysis, rather than a lander being limited to one spot. A rover would also be best for mapping how terrain and meteorological conditions change across multiple areas of the icy moon. Therefore, our group decided to extend our project and conceptualize a future rover mission on Europa. Our mission has several objectives. First, we want to collect data on the surface of Europa to detect molecules and organic compounds, such as carbon or sulfur, that can indicate life. Our group is particularly interested in the plumes on Europa, since they eject water from beneath the subsurface oceans. Analyzing the areas around the plumes can provide insight into potential biosignatures in the icy water. The rover will collect data from a variety of sample sites to provide information about the various regions and geological properties of Europa.
Finding life on Europa is a possibility because it fills the requirements of water, essential elements, and energy, components that are crucial for life on Earth. Water dissolves nutrients and enables chemical reactions. For essential elements, life requires an array of biological elements to serve as the basic building blocks and material for growth and reproduction. These include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. A Galileo flyby detected most of these within Europa. It is also possible that asteroids and comets could have impacted the surface and deposited even more organic or carbon-containing materials. Lastly, energy is dispersed throughout Europa's surface since Jupiter projects radiation onto it.
We chose the pool crater as our rover landing site due to the evidence of water nearby from previous flybys. It's one of the youngest craters on Europa, so it hasn't been wiped away by geological activity, and it still retains bright white rays of freshwater ice. We selected a northern region of the crater for our area of interest because of the plumes of water observed there in 2014 and 2016.
Land at 271.4 degrees longitude and negative 22.3 degrees latitude. This will be very close to an abnormally warm spot without landing on the rocky terrain of the crater. We had looked at multiple other sites with interesting areas, but due to a lack of information on the sites and the rough terrain, we had decided against them.
One of the biggest challenges with designing the rover was Europa's cold environment and icy terrain. While typical NASA rovers rely on a wheel mechanism called the rocker bogie, we opted for a new wheel design in which each wheel has independent mobility. This means it has a better range of motion to maneuver around obstacles in the terrain, which is particularly important because Europa's terrain is still not very well characterized. In addition, the wheels will have strong tread to prevent slipping on Europa's icy surface. As for the body of the rover, we chose a hexagonal shape so the rover would remain compact in order to keep the instrumentation insulated against the cold temperatures. To power the rover, we selected the battery used in the Dragonfly mission rover that will be launched to Titan in 2027. The battery is an RTG that will recharge a large lithium-ion battery and be held at the rear of the rover. Lastly, the rover has a drill to cut through the ice to collect samples and a robotic arm to aid in the analysis of said samples by the rover's instrumentation.
Rover instrumentation is often added in suites of 2 or 3 compatible instruments aimed towards one goal. The first 3 instruments we chose for our rover were for the detection of minerals and biosignatures. First, we have 2 different types of spectrometers. The mass spectrometer provides data, such as molecular mass, to interpret the elements and structures of the molecules making up the sample. The Raman spectrometer is a type of vibrational infrared spectrometer, meaning it studies the vibrations of molecules by recording what wavelengths of infrared radiation are absorbed, thus determining chemical composition of samples. Together, these 2 spectrometers should identify any signs of life at the molecular level in our samples. To provide visual context for the spectrometry data, the rover will have a microscopic imager to provide magnifying glass level detailed images of the samples. The next suite of instruments will provide data from the environment surrounding the rover in order to study the geophysical properties of Europa. This is important to understand not only as context for samples, but also for the growing fields of research in comparative oceanography and tectonics. The majority of environmental sensors on our rover are housed in one large instrument called the Environmental Monitoring System, similar to the one used previously on the Mars Curiosity rover. This provides a diverse array of meteorological data around the rover, including atmospheric pressure, temperature, humidity, winds, and ultraviolet radiation levels, as well as data on how environmental conditions vary across day, season, and location. The subsurface ice radar will use radar waves to probe under the ice surface and map the thickness of Europa's icy surface. This will give us a chance to study planetary geology and terrain across a range of meteorological conditions. The site imaging system will provide visual context for the variety of data being acquired. And lastly, the navigational camera will be housed in the same body as a site imaging camera, but use a different lens for a specific purpose, which is to give the rover the ability to drive itself autonomously.
Lastly, we have our conclusion, a wrap-up of our experiences.
One of the highlights of our SEAS journey was when the team was exposed to the real-life work of a NASA employee at the Johnson Space Center. Another highlight was when our team was excited to expand our project to encompass an additional research aspect, especially considering the future potential of this work.
How SEAS has inspired us. Before SEAS, I knew I loved programming. However, I didn't anticipate how fun it would be to combine programming with hands-on engineering to build our rover. Because of this, I've been inspired to pursue more hands-on engineering as a future career. I've also been empowered by the chance to participate in the full research process, work with incredible mentors, and get a sense of the exciting future work I could one day pursue at NASA.
As someone who comes from a community that does not have a lot of opportunities to pursue a career in the STEM field, I am extremely grateful for this opportunity to be a SEAS intern. This experience has not only opened my eyes to new possibilities, it has also secured my decision to continue to grow within the STEM field.
Being a SEAS intern was an incredible experience. Being here helped me secure my decision of wanting to be an electrical engineer. After being a part of this program, I grew to love all aspects of engineering more. Both the hardware and the software. I was able to grow my ability to problem solve and to engage in projects that I'm a part of, to give it my all and be a valuable member of the team. I now have a better understanding of how a team works and how every member is important and needed for the project to work successfully.
SEAS has been for me a life-changing experience. It was a wonderful opportunity to get more exposure to the field of STEM. I got to meet with very talented people who had the same interests as me. I was able to learn from my teammates and mentors. Some very useful skills I would like to mention.
I'm extremely grateful to have had this experience as a SEAS intern. Coming from a place with not many STEM opportunities, the knowledge I have gained from this program is once in a lifetime. I will continue to apply what I have learned this coming year and on to the future.
Through attending the SEAS program, I've gotten the amazing opportunity to apply the everyday subjects and knowledge I learned at school to real-world problems, such as using math for mapping coordinates and locating landing sites of Europa. Collaborating with great mentors and STEM-passionate students has inspired me to think outside of the box, and this internship has given me exposure to how useful and rewarding STEM can be.
The SEAS program has given me an experience I have never had before. It has allowed me an opportunity to communicate and collaborate on projects with people envisioning similar career paths as I am. It has opened up a wide new door of possibilities in the STEM field and has given me the resources and skills to be successful as I pursue a career in physics.
SEAS has given me an amazing opportunity to connect with like-minded individuals and enrich myself in new STEM subjects. After speaking with a mission control specialist for the ISS at Johnson Space Center, my eyes were open to new career options at NASA. Being a part of this program also taught me how to conduct scientific research and problem solve, which will be incredibly useful for my future career as a software engineer. I could not be more grateful. These are the sources we use for our research. We would like to thank some of the important people and programs that made SEAS possible. We would like to give a special shout out to our mentor, Ms. Crenshaw, and the Mars rover mentor, Mr. Ralston, who helped us with our rover conceptualization. We would also like to thank Patrick Petty and Sherelle Webb for reviewing our research abstract. And lastly, but not least, we want to thank Margaret Baggio and Selena Miller for running SEAS and making all of this possible. We could not do it without you.
Great presentation. You have several questions, so we invite you to please turn on your cameras and unmute. Our first question is, how is Europa different from Earth in terms of its ability to sustain life?
So Europa contains a lot of similar elements essential to life on Earth. There's water. The Galileo flyby has detected elements like carbon and phosphorus, and it has an energy source. So honestly, it would kind of be weirder to not find life on Europa than to find life there. But at the same time, this type of life is going to look a lot different than what we see on Earth. Since the environment is so extreme, only certain types of extremophiles would probably be able to cultivate there.
So the next question is, how did you determine what the weight limit is that your drone can carry?
So we first started out with a lander that was far too heavy, and we noticed that when we were trying to fly the drone, it would stay way too close to the ground. So we used a scale, and that first lander weighed 57 grams. So then we took off a few of the pieces from the lander, and we weighed it a second time, and it was 17 grams. And this lander was really light, so it would swing around a lot when we were flying it on the drone. So then we just went through the process a couple more times and added a few more bricks until we reached an optimal weight of around 27 grams, which provided the weight that made it not swing so much, but it was also not too heavy that it wouldn't impair the drone's flight.
And on your rover, you used a two-prong sample collection mechanism. What was the rationale for choosing a two-prong versus one prong?
I can answer this question. We designed the two-pronged lifting mechanism to maximize the efficiency of our rover. So rather than having to return to base every time it collects a sample, it returns after every 2 samples, doubling its efficiency. And this is something really important to consider, not just for simulated robotics challenges like what we did, but also for rovers on other planets. because in order to minimize the risk of getting damaged, rovers have to move very slowly. And in order to not waste time while completing scientific objectives, we have to make sure sample collection is as efficient as possible.
And what database did you use to select your landing site?
So I can answer this question. So for first, we looked through the NASA Solar System Explorer webpage and saw the different potential landing sites, such as like Pool Crater and Theramacula. Then, after canceling out the ones that had unsuitable terrain or that had little evidence of water, such as not being near plumes for ice, we narrowed it down to a few. And we looked through databases, such as there was one that was really suitable for Theramacula that was persuading us why we should use that one. It's called Science Potential from a Europa Lander, and it was called the Mary Ann Liebert publication. So, but yeah, we just used lots of data sites. So.
Awesome. And then what did you use as far as your programming language for your rover? How did you code and program it?
Okay, so I can take this one. So we use the Lego Spike programming software that's compatible with the model rover that we built in order to have the most efficient connection with the rover from the program and run into the least amount of glitches possible.
Perfect. Well, thank you all. You've done an amazing job. We appreciate your research and sharing your time and your talent today. Our next group to present will be the Artemis team. And with Artemis missions, NASA will land the first woman and the first person of color on the moon, using innovative technologies to explore more of the lunar surface than ever before. NASA will collaborate with commercial and international partners and establish the first long-term presence on the moon. We will use what we learn on and around the moon to take the next giant leap, sending the first astronauts to Mars. Leading the Artemis team was their mentor, Patrick Petty. So please join me in welcoming the Artemis team.
Hello, we are the Artemis team, and we are excited to be presenting to you this afternoon. During our research, we looked into the Artemis spaceflight program, which is designed to return humanity back to the moon and live on its surface long-term in order to apply our newly found information and research to the larger journey to Mars. After overlooking the previous Apollo missions and the Artemis 1 through 5 missions, we developed a proposal for the Artemis 6 mission. This includes all aspects of an Artemis mission. That'll be the Orion and SLS rocket systems to get to the moon and the Gateway module. The Gateway module that'll have the inhabitable systems and modules for the crew, and the landing site, which will be where the science experiments and research are conducted. Let's get started by introducing the Artemis team members.
Hello, my name is Alan Garcia, and I'm from Brownsville, Texas. I will be a junior this year.
Hello, my name is Diego Loa. I'm from Los Osos, Texas, and I will be a rising junior.
Hello, my name is Sebastian Centeno, and I am from Brownsville, Texas.
Hello, everyone. I'm Carlos Zambrano, and I'm from Brownsville, Texas.
Hello, my name is Daniel Trujillo, and I am from Brownsville, and I will be a junior this year.
Hello, my name is Diego Pruneda, and I am from Brownsville, Texas.
Hello, my name is Jacqueline Peña, and I'm from Brownsville, Texas.
My name is Ignacio Duran. I live in Los Frescos, Texas, and I am going to be a junior this year.
Hello, my name is Christopher Reynolds, and I'm from Los Fresnos, Texas.
The timeline for the Artemis 6 mission looks something like this. We expect the mission to begin in the year 2029 and launch during the month of March. The launch of the SLS will mark the start towards the Lunar Gateway. Once this has been reached, the astronauts will deploy 2 additional modules to the Lunar Gateway, the greenhouse and the bedroom module, which we will explain later. Once this is done, the landing crew will take the lunar lander towards the chosen landing spot and begin a 2-week period of deploying lunar experiments and conducting science. Once this is done, the astronauts will take the lunar lander back towards the Lunar Gateway and begin a 2-month period of analyzing the data they've collected and conducting further experiments on the Lunar Gateway. Finally, the astronauts will make the return journey back towards Earth and conclude the mission sometime during the month of June.
Our launch/landing crew will consist of a test pilot with an aerospace background, Jasmine Mobley, a geologist, Jessica Watkins, and a naval aviator with STEM basics, Scott Tingle. Now, our gateway crew, however, will have been there prior to the Artemis 6 mission, establishing a crew rotation among the rest of the Artemis missions to come. And the gateway crew will consist of a medic with a PhD, Johnny Kim, an IT manager with STEM basics, Warren Hoberg, and a Bostonist astronaut, Kajal Lindgren.
The Artemis 6 will use several key space vehicles to conduct its mission, this being the SLS rocket, the Lunar Gateway, and the Orion Crew Module. The SLS rocket used for the mission will be an upgraded version of the SLS-1, called the SLS Block 1B configuration. This rocket will use 4 RS-25 liquid hydrogen, liquid oxygen fueled rocket engines. It will also use 2 solid rocket boosters as part of its core stage. Altogether, they will produce 8.9 million pounds of thrust. Its second stage will use 3 additional RL-10 engines for a total of 4, each producing 24,340 pounds of thrust. This would allow the SLS Block 1B configuration to carry 38 tons of payload to the moon, 40% more than the SLS-1 module. After a several-day journey on the crew module, it will then dock with the Lunar Gateway. The Lunar Gateway itself will serve as a communication hub, laboratory, and temporary habitat for the astronauts staying on board. From here, the landing crew would take the lunar lander towards the chosen landing spot.
My partner and I worked on the architecture, environment, and living off of the Gateway. We try to make life on the Gateway as comfortable and as safe as possible. My partner worked on the sleeping quarters for the astronauts and the greenhouse. I worked on the panels and coverings for the walls. Safety systems present in this room are fire alarms, radiative detectors, camera systems, ventilation, and comms. The intent for these systems being present is to ensure that if an emergency were to arise, there would be some way of identification of the situation, a viable way of getting contact for assistance, and a possible solution to this emergency. One issue while on the Gateway is food supplies. The reason being is that when you restock up on food supplies, it takes 2 to 4 days before the food restocks and reaches the Gateway. While on the travel to the Gateway, the shelf life of the food will drop within that time frame. An innovative way to prevent having to resupply and the life of the food from dropping is using the greenhouse module. Greenhouse will be managed and can be used for studies by the botanist.
Going off what Ignacio said, there are going to be 2 modules added into the Gateway before the mission begins. 2 modules that will be added are a bedroom and greenhouse. The main focus on the living quarters are to make it as comfortable as possible for the astronauts in the Gateway. Most astronauts don't have the luxury of having enough of a cubicle space for sleep when in orbit. Bedroom module will provide a place to sleep for long periods of time with an ample amount of space, ensuring safety and comfortability. The safety and comfortability will be possible due to the multi-layer that is laid across the entirety of the room, including the beds. Giving a designated place for all crew members to meditate and sleep will help to improve mental, physical, and social health. The module has a total of 6 beds to maintain up to 6 crew members at a time. Now to go further into the parameter of the bed module, the bed module interior will be composed of a multi-layer fabric. The fabric will consist of the following: Griswold, flame-safe neutral rubber, Paran 4701-30 polyurethane, Visco BF 1000 extra soft silicone foam, and synthetic viscoelastic urethane polymer. The purpose of each of these materials is to make a safe and comfortable cushion to sleep on and impact into. The flame-safe natural rubber is a layer purposefully implemented to prevent outside fires harming the crew inside the bedroom module. The industrial polyurethanes is a fill layer to take a load of force from the collision into the wall. Visco BF 1000 extra soft silicone foam and a synthetic viscoelastic urethane polymer are upper layers to make the padding a suitable mattress for the bed. The greenhouse module will be made up of transparent fused silica and borosilicate glass panels and double pane tempered glass vacuum sealed together with a film of polycarbonated glass in the middle of the vacuum. The transparent fused silica and borosilicate glass will be covered with a fine layer of filament or plaster of clear fiberglass to prevent radiation from the sun degrading the fused silica and borosilicate glass. Fiberglass has been proven to prevent from radiation from the sun affecting the surface of glass. If one of the 3 panels breaks, there would be no chain reaction with all the panels of glass to break, and the pressure of the gateway would not change. On the outside of the greenhouse, there are steel bars to hold different sections of glass panels. The same gray tubing allows for attaching covers to hold onto the greenhouse. In certain times of the year, a cover would be developed to enclose the greenhouse for a particular reason, to not harm the plants from overheating or accumulating too much sunlight. Dark color rods in the interior is a stainless steel pipe countertop that is used to pump nitrogen at different temperatures, if need be, around the glass panels when needed to cool or heat the glass. The same countertop can be used to grow plants above or on. The additional materials will be needed to complete the greenhouse, such as tables or cubbies.
The landing site. The Shackleton-Degerlache Ridge is located on the south pole of the moon, in between the Shackleton and the Degerlache crater. The ridgeline is roughly 14 kilometers long and has a relatively flat view, which will allow astronauts to get a perfect line of sight into the crater. Landing on the south pole of the moon will give astronauts access to volatiles such as ice water, solar energy, and communication with mission control. The ridge contains blocks ejected by the Shackleton impact event that could reveal regional lithology, the age of Shackleton, and South Pole Aitken Basin, making them primary targets for geological exploration.
This is a brief introduction for a scientific experiment topic. The main reason for this inclusion of scientific experiments is that we want to explore and grasp a better understanding of geological and biological conditions that the moon has for building a base, and further research on the moon in the following years. For Artemis, we want to do as a priority to expand mankind's knowledge of space. So we want to take advantage of the many Artemis missions to study the moon, and in the future, Mars for a safer and knowledge expanding of the universe around us. We wanted to have at least one scientific experiment for biological and geological experiments. So for a biological aspect, we chose the Lunar Explorer instrument for space biology application, or LEA for short. This experiment is about finding the effects of the lunar surface on yeast, which can be expanded upon using bacteria and human cells to understand how living organisms react to lunar surface conditions. For the geological aspect, we choose the terrestrial laser scanning to create a geographic map of the moon, and later in the future, the Mars that can allow astronauts to view the topographic of about 200 meters or 219 yards around them. And to go along with this experiment, we choose to handle X-ray fluorescence spectrometer to scan rocks and soil samples to find their composition. Another experiment that is part of the geological aspect of the instrument, the heat flow experiment, or FEE for short, is an experiment that will be conducted to find how much heat is lost from the interior of the moon that is being released from the core of the moon, and continuing the research of finding the overall heat flow rate of the entire moon for an updated understanding of the moon. This information can be used to understand how the lunar surface can be advantageous for underground bases in the future. It can also contribute to surface bases and scientific experiments that can rely on the heat being released as an alternative power source.
The solar wind spectrometer measures the energy, density, and direction of travel of solar wind. This experiment will give astronauts a method of studying the general properties of solar wind and its interaction with the moon at the lunar surface. The Charged Particle Lunar Environment Experiment can provide data on the energy distribution of solar particles and their effect on the Earth-Moon system. This experiment can be used to measure the particle energies of solar protons and electrons that reach the lunar surface. The Modal Optimized Vibration Dust Eliminator, or MOVE, is an active dust mitigation system for thermal radiators that uses vibrational excitation at targeted modal frequencies in order to mitigate dust adhesion with the assistance of passive dust mitigation coatings. The Lunar Active Seismic Experiment can determine the detailed structure of the lunar crust using seismic waves measured by a network of geophones. This experiment can be used to evaluate the lunar surface for future large-scale construction. The Lunar Dust Detector can be used to measure high-energy radiation damage to solar cells, reduced solar cell output due to dust accumulation, and reflected infrared to compute lunar surface temperatures. This experiment will give astronauts a way to monitor the long-term degradation of solar cells from radiation and thermal effects. Conducting this collection of experiments in the lunar environment would contribute to the scientific return of the mission, as they each serve a specific purpose towards the mission success.
The XEMU EVA suit is NASA's in-house upgrade to the previous EVA suit, the EMU. The EMU has an EVA time of 9 hours, and a full upper and lower torso movement, which in turn removes the bunny hopping issue that astronauts normally face while on the moon. The way astronauts enter the suit has been changed to a new rear entry system, and the entire suit has been changed to a new modular design that allows for in-flight maintenance and component upgrades. Along with all of these new changes, the new technology has been added to the suit, allowing for high-speed transmissions of audio and video from the suit. All of these changes together should allow for the XEMU to be traveled further in and work for longer hours than its predecessor.
Introducing In Situ Research Utilization, or ISRU. Artemis 6 will include a rover concept capable of carrying and deploying a scientific payload. Pictured below is the system's architecture of an integrated rover body. There are 2 radio frequency demonstrators and an ISRU demonstrator stored as payload. 4 scientific experiments consisting of 2 spectrometers, a rock abrasion tool, and a microscopic camera are also carried. Its primary objectives are set to initiate and complete within 1 lunar day. It is designed to test the feasibility of in situ utilization of a lunar regolith. About 4,200 grams will be collected. The ovens of the ISRUD will heat up the regolith for chemical analysis and elemental composition detection. In further commercial contracting, Paragon and Grindr announced a system of ISRU-derived water purification and hydrogen-oxygen production, or the IHOP. Artemis 6 will focus on the first implementations of combining critical ISRU functions. IHOP is designed to derive water from the ice caps found in permanently shattered regions of the lunar poles. It processes and purifies the water of corrosive and volatile contaminants, then electrolyzes the water to generate hydrogen and oxygen for propellant. Optimal use of such outputs could be seen in fuel cells, crew atmosphere revitalization, and crew portable water. Artemis 6 will include commercially contracted lunar terrain vehicles, or LTV, to provide astronaut mobility and payload services for added range and efficiency of experiments. Pictured below is a rendition of the announced partnership of Lockheed Martin, General Motors, and Goodyear, to which they collaborated on creating a lunar terrain vehicle capable of using natural feature tracking such as seen in the asteroid mission OSIRIS-REx. Some design concepts of the LTV, as released by GM, include Ultium battery and Ultium motors. This mission will also proceed with the beginning stages of the surface habitation, or the SH. It will embody self-sufficient power generation and storage, ECLSS, as well as the inclusion of surface, orbital, and communication assets. Within its early stages, it is proposed to hold 2 crew members on a 1-month excursion. However, it could be developed to twice the housing period and occupancy. It will consist of a vertical 2-story construction, which encapsulates a metallic core and a lower hatch for EVA operations. Its boundary layers are made up of environmentally resistant layers, MMOD, and MIL.
The ECLS, or the Environmental Control and Life Support System, is the water and oxygen filtration system aboard the ISS that allows the reuse of water by filtering it to a state where it's clean enough to drink again. Since the ECLSS has proven to be a useful resource on the ISS and has been proven to work for up to 14 astronauts at once, we believe that this system would be a great fit for the Gateway. Waste buildup on the Gateway is a prevalent issue because normal procedure is just to send it into Earth's atmosphere and burn it up. However, since Earth is too far away, there really is no way to get rid of the astronauts' waste. As a solution, however, a biomass generator can be added to the Gateway in order to work around this issue. Waste is put into a combustion chamber where it burns up and heats water up, which in turn turns a turbine with the intent to create power. Electricity produced by this can be used on the Gateway for other systems.
The scientific gain. We hope to gain a chance to study the geology of the moon's surface to reveal any hotspots that correlate to the research to Mars. Moreover, we wish to see the limitations of our crew, given the fact that half of them will be on lunar orbit for several months, testing new modules to see what we can provide and improve on. The return. The Meta Team Gateway plans for returning to Earth is by translunar injection from the Gateway. The crew will power on the Orion and inject from the docking ports, then use engine bursts to put them on the correct path back to Earth. Throughout this time, the Orion will continue to make small adjustment burns to the trajectory to ensure that the crew has a safe trip back to Earth. It will enter the Earth's upper atmosphere using the atmosphere and lift of the crew module to bounce out of the atmosphere and finally descend. Since it will be traveling at speeds roughly 20,000 miles an hour, the Orion will make a rotation that will put the nose of the Orion in upper position. This will enable some drag, which will allow us to deploy the parachutes, slowing down the Orion from 20,000 miles an hour to roughly 20 to 30 miles an hour for splashdown. Waiting at their landing spot will be a naval ship that will take them home safely.
After completing the SEAS internship, we found the obstacle we faced the most throughout our mission planning was maneuvering between feasible and unattainable concepts. Because the Artemis missions are currently ongoing, many of our requirements are still under development and testing by NASA and commercial contracts. So we had to essentially meet in the middle for Artemis goals and executional milestones.
In impactful takeaways, the SEAS project benefited our team profile because we all applied under interest in aerospace or mechanical engineering. Working together gave us exposure to the different aspects of mission requirements and subsystems. The SEAS internship helped sharpen our perspectives on collaboration and future career interests.
We from Artemis would all like to give a special thanks to the SEAS program, Texas Space Grant Consortium, the Center for Space Research, and NASA for allowing us to be part of this wonderful opportunity. And we would also like to give a special thanks to our mentor, Mr. Petty.
Great. We'd like the Artemis team to please turn on their camera and unmute. We have a few questions for your team. So in the overall Artemis plan, how does this mission relate to the scale of the entire Artemis habitation of the moon?
I can go ahead and answer this one. So when it came to defining our project, Artemis 6 is the configuration to the beginning prospects of lunar settlement. It is basically where we say we're here to stay and this is how we're going to go about it. So, and it's apparent in our utilization of our in situation resources. We actually begin the construction of our surface habitation and our greenhouse. And it's also apparent in our scientific experiments that we had decided on. So it's like saying we have our eye on the target and these are going to be our beginning steps.
And how do you think this mission will help NASA reach its goal of going into deep space and onto Mars?
So I can answer this question. Basically, with the research and sciences that we'll be conducting on the moon, we will be able to apply to Mars, since it'll be the first time that we go into deep space and understand what our limitations are and what we can do.
Great. So how did you select the scientific experiments that would be flown on this mission? And why would you select ones over others?
I can answer that. What we chose is basically we wanted to specific experiments that actually help benefit taking advantage of this mission. And what I wanted from it was basically just at least one biological and at least one geological. It's because this way we had been in the moon previously, but we haven't anymore. So we want to at least get information of how cells react, basically starting with yeast and probably starting on with human cells and how they will react to these conditions, these new conditions that our bodies have never been there previously. And we want to continue conducting geological experiments, helping probably finding the origins, how this planet was formed, the materials it was made of, to get a better understanding of the universe around us. And so I wanted to me and Carla, when we were choosing the experiments, that's when we wanted to conduct these type of experiments to take advantage of this mission and help expand our knowledge of the universe and the planets we're going into.
Great. And how did you choose suitable materials to build the gateway?
Okay, so I'll take this one, and I apologize about my video. So with the materials, how I selected them were based off from previous things such as the cupola. I took the glass panels that they have there, the silicate and the fused borosilicate, and put that on the greenhouse because we know that it works. And we just started adding layers into it to make sure that it does maintain a safe pressure and allows a good amount of sunlight to the greenhouse and a filament of carbon fiber to prevent radiation affecting glass. Now for the bedroom, I only talked about the interior. I didn't talk about the exterior because I had no clue how they would encase this. And I could have gone further into that, but I didn't have enough time to discuss about it. And I apologize about that. But the interior, I did select them for specific reasons for considering impact collisions of the human body to a cushion. And that's pretty much it.
Well, your team did an excellent job. Thank you for your research. And we're looking forward to learning more about the Artemis mission in the future. So our next SEAS team is the High Altitude Ballooning Project. During this project, students developed a small engineering payload that was deployed on a high altitude balloon. Working with their mentors, the team developed the payload along with the supporting electronics and systems required to conduct a test with a given sensor. Students developed a hypothesis, an experiment design, and then analyzed the data after recovering the payload. A special thanks to Dr. Brandon Jones and graduate student Rachel Gold for their guidance and leadership. So please join me in welcoming the BLAST Balloon at Low Altitude Studying Temperature team.
Hello, everyone, and thank you so much for coming. Our group name is BLAST, and we've studied Balloon at Low Altitude Studying Temperature. Now let's meet the team.
Hi, my name is Anjul Save, and I'm from Austin, Texas.
My name is Fiora Brantahani, and I'm from San Jose, California.
My name is Hayden Thompson, and I'm from Oakland, California.
My name is Jamin Sia, and I'm from San Jose, California.
Hello, my name is Kathleen Cravens, and I'm from Lakewood Ranch, Florida.
And I am Seth Cohen, and I'm from Los Angeles, California. Throughout the course of this project, we had the privilege to work with our mentors, Dr. Brandon Jones, an assistant professor in the Aerospace Engineering Department at UT Austin, and Rachel Gold, a PhD student studying orbital mechanics at UT Austin.
Now we will walk you through the significance of our work. In this process, we really wanted to prioritize engineering exploration, and we were able to encapsulate the essence of electrical, mechanical, and aerospace engineering all into one project. And through the use of data collection, we wanted to understand more about physics and theoretical analysis behind climate science. For our background, I will take you through some of our project structure and goals. So for our mission level objectives, we wanted to prioritize both understanding and application of new scientific concepts. So first, we sought to understand the variations in the temperature based on altitude. And we did that with the goal of verifying theoretical variations in temperature based on the Earth atmospheric model.
Now let's get to the approach. We followed the NASA systems engineering process for the design of our project. NASA's online modules helped to educate us on the process. Then we had to brainstorm risks and ways to mitigate them. We made a risk chart as shown here to compare the likelihood and severity. For example, in order to mitigate the risk of electrostatic discharge, which could shock and damage our sensitive electronic components, we wore ESD bracelets while working with the parts.
Our system consists of the balloon and the banana. The balloon refers to the weather balloon itself and the tether between the balloon and the banana. The banana is the structure and everything within it.
We split up our system into 7 subsystems and came up with requirements for each subsystem.
As part of the NASA systems engineering process, we filled out a requirement verification matrix. This diagram shows a hierarchy of requirements. The mission objectives instruct the system requirements, which inform the subsystem requirements. We've included an example regarding temperature collection.
For the command and data handling subsystem, I researched potential microcontrollers and I weighed the benefits and downfalls of the different options, ensuring that they fit the requirements we stated earlier. I ended up deciding on the Adafruit Feather M0 Atalogger because of its ability to store data on a microSD card without an outside extension, as well as its capability to use I2C wiring, among others. After selecting a microcontroller, I wrote code to test it and its compatibility with the sensors. I tested its ability to store data on the microSD card and to read measurements from the sensors, and I also tested how everything worked when it was integrated together. In addition, I wrote the program for the experiment mode, which collected data during the launch of our balloon. The photo on the left is a test that we were conducting using a breadboard before we were able to solder everything. The photo in the center is of the data that was collected during the freezer test, and the photo on the right is an Arduino program written to test the ability of the microcontroller to store measurements on the microSD card.
So I was in charge of payload, and I researched the temperature and altitude sensors that we would use for data collection. Based on measurement accuracy and microcontroller compatibility, we decided on the sensors up on the screen. The diagram on the right is the wiring layout, and the bottom left photos show the sensors within the structure. We decided not to use a breadboard in our final product in order to minimize the banana size and weight.
I was in charge of the thermal protection system and the environmental protection system, both of which require a lot of risk analysis. And I sought to protect both the interior and exterior of our system. Something I focused on a lot was actually the wind's effect on altitude. So if you place your attention to the image on the right, the red circle, the larger red circle, represents our balloon, and the blue squiggly lines represents wind. And the force diagram right next to that essentially depicts what would happen if wind acts upon our system, which in this case tilts the balloon to the right and knocks it off its original trajectory of pointing straight up. So since wind would be acting upon the balloon in our launch, I constructed a Python program to account for this. So at the bottom of the screen, you'll see an image where this Python program takes in user inputs. And for the estimate, I used 2.7 meters per second of wind, which is roughly around 6 miles per hour of wind. And we wanted to reach 1,000 feet with our system. So the system is telling me I would need around 1,107 foot of tether in order to reach that desired altitude of 1,000 feet. So I made an official recommendation to extend our tether in order to reach this desired altitude and add up to 10% to our original tether length.
Now for the MGSE and EGSE, which stands for the Mechanical and Electrical Ground Support Equipment. One thing I was in charge of was the ground test procedures and code. And based on the requirements and necessary tests for all subsystems, I designed integrated test procedures and wrote code to test the sensors and the expected function of the hardware in the banana. I was also in charge of the data analysis and the ground station computer. So I wrote Python code in Jupyter notebooks to calibrate the sensors and analyze gathered sensor data. Here's a sample plot from a temperature sensor test while we were at the launch site. I also operated the ground station computer, which was for quick data analysis at the launch site.
For my subsystem, which was electrical, I had to calculate the power budget by researching and selecting sensors with CDH and payload. After selection, I had to calculate the total amount of volts, amps, and watts that were needed to supply the system. From there, I selected a battery that would meet this requirement. Before integrating the battery, we had to conduct tests with a multimeter to ensure that there was resistance in the battery. After testing the battery and integrating the circuit, we tested the connections between the sensors and the microcontroller to make sure the correct connections showed resistance.
Regarding the structure, I needed to design a case that would store all of the necessary components. I used the 3D modeling software Onshape to create a structure that was eventually 3D printed. Included above are some photos of the design as well as the final product. For our control and guidance of the balloon, I had to first determine the right amount of helium required to produce positive lift. I used the number 100 grams as my starting value for the lift required. I created a calculator which would take it in the different weights of the equipment that we used and determine how much helium was necessary. After that, I had to effectively secure the tether to the ground and determine a method of increasing altitude in 50-foot increments. In the middle photo of the slide, you can see the calculator that I used to determine the helium requirement. And in the photo on the right, you can see me securing the tether onto the ground.
We performed a number of additional tests and procedures to try to ensure as successful of a launch as possible. We tested all of the systems integrated together, as well as a few calibration tests, such as a freezer test and a drop test. Through these tests, we verified that our sensors in our system all worked correctly and that we accounted for any error or variation that we would be seeing in the data on launch day. We also tested our parachute to confirm that it would work correctly for the launch.
One of the integrated tests that we performed was a freezer test. In this test, we tested this temperature sensor by putting it in a freezer. Since the temperature took some time to go down, a least squares exponential fit of the error of the temperature measurement compared to the freezer's display temperature, which was -15 degrees Celsius, gave us a good calibration result. We can see that the sensor has a small bias from the true value, since the error was exponentially approaching 0. And the sensor precision matches the standard error of the residuals of the measurements, which means that through testing, we have confirmed the precision of the sensor. Another integrated test that we performed was a drop test. In the drop test, we released the banana from the 4th floor of the CSR to simulate using a balloon to move the banana through different altitudes. We calculated the standard deviation of the temperature at each measurement stop to compare with the sensor precision.
Now let's see what happened. Before the launch, we had to calculate the helium, do a ground test of the payload sensors, secure the banana, and deploy the balloon. During the launch, we went to an open field at the J.J. Pickle Research Campus. Here on the left, we can see Seth attaching the banana to the balloon to prepare for the launch. In the middle, I am carefully releasing the tether at 50-foot intervals in order to ensure that the sensors have time to collect the data. On the right, we can see our balloon flying high in the sky.
Unfortunately, after collecting the balloon and checking the data, we found that we had only collected 40 seconds of data instead of the 90 minutes of data that should have been collected from the launch. After some analysis, it was evident that this data was taken at the beginning of the launch, after unplugging the USB cable and before we let go of the balloon. We now needed to determine the exact cause of this data loss.
Given the contrast between our previously successful test and our lack of data collection during the launch, we have to ask the question of what went wrong. On this slide are 4 key factors that we believe led to the lack of data collection. First was wind. The estimated wind was around 6 miles per hour prior to the launch. However, during the launch, the wind speed was around 5 meters per second or 11 miles per hour, nearly double of what was previously estimated. We believe that this wind may have moved our electronics, including the micro SD card, which held our data. Additionally, during the launch, the temperature was around 105 degrees Fahrenheit, so our system could have possibly overheated during this time. Additionally, the battery may have discharged, or we might have faced code compiling or uploading issues.
So what could we have done differently? Well, if we were to run this experiment again, ensuring that we did collect data, here's some things we would do differently. We would launch the balloon earlier in the morning because that would reduce wind and lower the temperature, reducing the possibility of failure due to either of those factors. In addition, we might downlink data to the ground station in order to check data was actually being collected or to check system health and function. Another idea of something we might change, were we to run this experiment again, is to go up to a lower altitude, say 200 feet, then come straight back down to ensure data was being collected. The last thing we could do was to add an LED indicator to flash when data is being collected. This would give us a visual cue to make sure that data collection was taking place.
So this section is about our reflection on our project and on the entire SEAS experience. Beside the lack of data collected from our flight, we faced a nationwide helium shortage at the start of our project, so we weren't even sure if we were going to launch. Some of our alternative ideas were releasing the banana off the building or using a drone. Luckily, however, we were eventually able to secure helium. Additionally, we also only had one chance to print our structure, so we had to work around a few problems. One of which was that there was no space to connect the components using jumper wires. So we had to solder wires directly to the microcontroller and sensors. Also, we had to remove the lid of the banana at the launch because the temperature sensor was providing inaccurate measurements.
Now that our project is complete, it is time to reflect on our SEAS experience. I am Anshul, and I'm an aspiring computer science and computer engineering major. And this program has helped me learn more about the different potential STEM fields, as well as to delve deeper and improve my knowledge about certain things within those fields, such as working with electronics. My favorite part of this internship was being able to physically create something and seeing our design progress through the phases of the NASA systems engineering process. I really enjoyed being able to collect real-time data during our tests and analyze and improve upon it.
I'm Fiora. C solidified my decision to pursue either mechanical or electrical engineering because I really enjoyed working on sensor integration through a hands-on project. I also liked all the team building activities that were provided by C's that helped me develop a close bond with my teammates during this short period of time.
I'm Hayden, an aspiring computer science and mechanical engineering major, two areas that I got to explore further during this internship. Two of my favorite memories of the C's internship were Dr. Hun Mandel's talk, including when I got to speak with him afterwards about the privatization of space travel. I also thoroughly enjoyed our tour of UT Invention Works, where they had a plethora of 3D printers, laser cutters, and student projects on display.
I'm Jamin, and I aspire to be an electrical engineer major in the future. Going through the entire engineering process from start to finish has expanded my knowledge and experience in engineering and programming. One of my highlights from C's was learning new Python libraries for statistics, which will be useful for future work in engineering and data analysis. I also enjoyed Dr. Carl Gebhardt's talk on black holes and dark energy and his work on head decks.
Hello, I'm Kathleen, and I'm an aspiring mechanical and aerospace engineering major. And C's has helped me to dive further into the engineering process and deepen my interest in aerospace. My favorite part of this experience was talking to a former C's intern at the Johnson Space Center. It was so fascinating to hear about his experience as an intern at Johnson, and I hope to be able to follow a similar path in the future.
And I am Seth, an aspiring mechanical engineering major. And I think that C's has provided me with the opportunity to use the mechanical engineering process, incorporate scientific research, and develop a real-life project to accomplish a given task. My highlight of the entire program was our tour at the Johnson Space Center, where I was able to view cutting-edge research and meet with scientists who are doing exactly what I want to do in the future.
So congratulations to the BLAST team. I invite you to turn your cameras on and unmute. We have several questions for the team. The first question is, why did you call the device a banana? And how did you come up with that name?
Yeah, I can take this question. I think when we were working on the project, there was a lot of confusion between us referring to the electronic components inside of our project and the structure, including the electronic components. And so we wanted to differentiate the two. And so when we first went about working on the project, we called only the electronic components the payload. But when we had to refer to everything beneath the balloon, we needed a new name for that. And so basically I was eating a banana at the time, and so I called it the banana, and then the name stuck well.
So how much time did you spend preparing for your mission? Would more time have helped with your data collection?
I can take this one if that's okay. Well, I believe that we initially started off planning it like from the 2 weeks before we actually came there, and then we spent like the entire first week up until Tuesday working to plan using the systems engineering process. I believe that if we had like maybe an extra day to run some more tests and work on the hardware, it might have helped a little bit more. And also if we had been able to launch in the morning instead of the afternoon, because it was like 105 degrees out and the winds were really strong at that point. So if we'd been able to launch earlier in the morning, I feel that that probably would have helped our chances with getting more data.
And why did you make the switch from a high altitude balloon to a low altitude balloon?
So it's based on like the time frame, because one of the most important parts of our project is recovering the payload, because that's where we get all our data from. And with the high altitude balloon, that's not necessarily guaranteed. So yeah, with the low altitude balloon, we can attach to a tether to ensure that it comes back to us. And also to get a weather balloon over 1,000 feet, we'd have to get FAA approval. And yeah, with only like 2 weeks to get that all figured out, it just was more practical to use a low altitude balloon.
And I think that you covered this in your presentation, but what do you think was the primary reason for your lack of data collection?
So we had performed a number of tests before our launch, and they were all successful. And we also performed a number of tests after our launch to see what might have went wrong. And that helped us eliminate a lot of possible reasons for the loss of data. So we think that one of the main reasons for the loss of data was overheating of the banana and the systems because of the extreme temperatures that were outside during the launch, and that could have contributed to overheating of the battery or the microcontroller. And also the significant wind speeds, because as we had mentioned in our presentation, the wind speeds on the day of the launch were significantly higher and stronger than what we had used in our calculations previously. So we hadn't done a lot of testing regarding wind speeds that strong. We had done like a few shake tests and stuff, but they didn't account for the damage that could have happened to our instruments.
Well, you did an amazing job, and we appreciate you sharing your research today. So our next project is the Astronaut Photography Program. NASA monitors our dynamic Earth using a variety of assets, from Earth-observing satellites to astronaut photography taken by the crew on the International Space Station. During this project, interns worked with the astronaut photography of Earth to gain experience with research, communication, and creating content aimed at producing a product that will enable the public to learn more about our planet. Thank you to Rosina Miller from the NASA Astromaterials Department at Johnson Space Center for her guidance and enthusiasm mentoring this team. So please join me in welcoming the Observing Earth from Space, using astronaut photography to analyze geographical climate patterns team.
Welcome to our 2022 NASA SEAS Astronaut Photography Team presentation. We would like to welcome NASA professionals, TSGC representatives, subject matter experts and mentors, all student teams, educators, and invited guests. And this is who we are.
Hello, my name is Ado Nathani, and I'm a rising senior from Lane Creek High School in Houston, Texas. I aim to pursue a career in mechanical or civil and environmental engineering.
Hello, my name is Adele Wilson, and I'm an incoming junior from Claremore High School in Claremore, Oklahoma. In the future, I hope to pursue a career in either engineering or biomedical science.
Hi, my name is Annabelle Wang, and I am a rising senior at Westview High School in San Diego, California. In the future, I hope to pursue a career in civil engineering or architecture.
Hi, my name is Rishi Iyer, and I'm a rising junior at Wheaton High School in Rockville, Maryland. In the future, I aim to pursue a career in space science and chemistry.
Hi, my name is Hannah Norris, and I'm an incoming senior at Prosser High School in Prosser, Washington. I aim to pursue a career in astrophysics and communication.
Hi, I'm Arnok Chitari, and I'm a rising junior from Westwood High School in Austin, Texas. I would like to pursue a career in data science and urban science.
For our 2022 NASA SEAS project, we explored the vast reserves of astronaut photography accumulated by NASA over the years and discovered its immense underuse. We found that these untapped images captured by astronauts aboard the ISS include a wide array of features on Earth. From ancient cities to uncharted reefs, our work not only showcases crucial insight into the makings of our planet, but also has the potential to serve as an educational tool that can spark interest in the minds of our youth. Our mission is to be a part of the road that is paving the way for scientists to create technologies that can help to study short and long-term environmental impacts, as well as use the data obtained to implement strategies to discover more about our planet.
By sharing these images in an engaging way, we realized that we could provide a powerful medium for learning about geography, show an influential perspective on the impact of climate change, and, most importantly, illustrate the importance of an underlooked role an astronaut may play. This helps provide a deeper understanding of the intricacies of space research and presents to kids that you do not need to be a scientist or an engineer to have a place in the future of space exploration.
Our team came to the conclusion that creating an interactive game called Where in the World to be featured on the NASA website would be the best way to accomplish our listed goals. Using pictures taken by NASA astronauts, we created a trivia game where students can gain knowledge of important geographical features and have the unique chance to see familiar features and cities from an astronaut's point of view.
As shown here, incorrect guesses elicit hints that redirect the player towards the right answer, while correct ones prompt fun facts about the location in the photograph. These responses provide further opportunities for learning and engagement and create an immersive, responsive experience.
As the world urbanizes, more and more people are moving into cities. While the natural features of our world receive lots of scientific attention, we felt that cities have lacked the urgency of study that they require. A majority of the world will soon call a large city home, and astronaut photography gives us the opportunity to protect our homes. Being man-made, cities are extremely susceptible to natural disasters and the consequences of climate change. We must monitor them to the best of our ability. Rising sea levels in places such as Miami, Shanghai, and Bangkok, and extreme natural disasters caused by climate change in cities like Jakarta and Lagos are just a few of the often neglected issues that analyzing astronaut photography offers insight to. Through our analysis, we found commonalities among many cities in how they were constructed based on factors like when they were formed and how many people they were intended to support. These conclusions helped us understand cities further, the same way our players will be impacted in their understanding.
Now, to take a look at our process, we first sifted through resources such as a gateway to astronaut photography to curate a collection of 30 images that best illustrated unique features such as rivers, seas, mountains, and more that surround the cities. We then found and labeled important features to aid the player in identifying the location. By utilizing Google Earth and the latitude and longitude provided with the image ID, we were able to approximate the north orientation of each image and display that as well to make it easier to comprehend each photo. After that, we researched the city to create hints and to offer fun did you knows about each correct answer. The hints are supposed to narrow down the choices but not completely give away the answer. The did you knows would be a fun, memorable fact about the city's history and landmarks to further educate the learner about it. After collecting all of the facets needed for each slide, we'd link answer choices together in Google Slides and transfer our project to external softwares to incorporate food animations and transitions.
In the process of curating images, we faced a unique issue of uniformity among cities. While natural features are sporadic and therefore often distinguishable, cities are man-made and many present similar layouts and structures. This forced us to look far and wide to ensure that each included city served a purpose and gave some sort of unique insight on different fundamentals of cities. To combat our issue of uniformity, we developed a process to identify rivers, landmarks, and other important features that can differentiate cities from one another. We sifted through dozens of images to make a collection that best represented the aspects we wanted to showcase in our game. This helped us clearly define important parts of an image and aided us in creating labels. All in all, we wanted to select a topic that was widely accessible, yet often underlooked. This presented its own set of challenges that we had to work together to overcome.
Here is an example of one of the questions. As you can see on the left, the image is here with the label of a river. This label provides a clue regarding the main language in the country and also the terrain. The north orientation allows the user to get an idea of where they are to help identify key features. Also, by using the luminosity of the city lights in the night, you can tell how developed and how large it is. On the right, we have 3 answer choices to choose from. Below the choices is a button that shows 2 hints. These hints can help you eliminate answer choices. By using the hints, labels, features, and north orientation, the player can find the answer and also learn a fun fact about the city. Using process of elimination, Rio de la Plata is in Spanish, so we can eliminate Canada. Miami could still be possible, but the hints narrow the answer down to Buenos Aires. Here, we included a daytime photo. It can be a little harder to identify how large or developed it is, but there's a major river that runs straight through it. We can identify this river and use a language to help us. Along with that, the hint says warmer climate, so we can conclude that this is Bangkok. By using features throughout the quiz, players will be able to learn something and also have some fun.
Hannah and I decided to explore impact craters specifically because we felt this type of geographical feature is often overlooked. We frequently associate craters with planets or extraterrestrial objects that lack the protective atmosphere we have here on Earth. For this reason, we wanted to explore significant craters on our planet. Despite serving as crucial windows into our planet's past and future, craters frequently go unnoticed by the public. Impact events are a fundamental part of our planet's history, influencing climate and life forms. Through studies on impact craters, we can determine the age of sediment as well as extraterrestrial materials.
A lot of the work we had to do wasn't difficult necessarily, but certainly time-consuming. It took a while to sort through the photo databases to select the best images, gather all the information we needed for our hints and did you knows, and assemble everything into our presentations. The primary database we used to find images was NASA's Gateway to Astronaut Photography. We sorted through the crater photos to find unique and interesting images that would appeal to our intended audience. We also conducted research on the craters themselves, noting down their location, age, and other interesting facts unique to each impact.
Using this information, we curated 2 hints per image that learners could use to help them pinpoint the location of said image. We also searched for information on the crater that was particularly interesting to keep students engaged when they answer a question correctly. These were used as our Did You Know facts. We assembled the initial drafts of our activities in slides, using the hyperlink feature to make the questions interactive. The linking process was quite time-consuming, as each of us had 70+ slides to weave together, and each slide was unique.
One of the challenges we faced was learning how to identify the key features of the photographs we were using so we could match them to the models we found on Google Earth and identify which direction was north. Depending on how eroded the crater is, or how any lakes surrounding it have shrunk or grown over time, matching up the key features could prove quite challenging at times. Some craters have been better studied than others, meaning that it was extremely difficult to find information about some of the craters we included. But we persevered and found the data we needed.
Some of my favorite craters include the Lonar Crater and Oasis Crater. Each of these impact craters are unique depending on the size, shape, speed, and age of the crater. Not only do these factors influence the impact crater formed, but the contents of the surrounding sediment also play a role in the remnants of the impact crater we see today. With the Lonar Crater, I was most drawn to the nearly perfect circular shape of the impact site, as well as the depth that can be seen from as far as space. The meteorite impact that created this crater is estimated to have occurred from 35,000 to 50,000 years ago, which is relatively recent when it comes to the history of our planet. This is one of the reasons why the crater seems so well defined.
My favorite of the images I used for my project is Glikson Crater in Australia, also known as the Shoemaker Crater. I chose my craters because I found their photos to be unique and eye-catching, especially Glikson Crater. Because it's so heavily eroded, it doesn't resemble your typical crater. Its photo reminded me of an abstract painting when I first saw it, and I find it really cool that a structure like it can exist on Earth.
Since your average person probably isn't going to be familiar with craters, we decided our hints should focus more on the surrounding region, clues that people could use to eliminate one or more of the answers with a little knowledge of geography. Many of our Did You Knows are facts we found interesting, but ultimately too obscure to serve as a viable hint.
I hope students will come away from our Where in the World projects with a more extensive knowledge of Earth's craters, as well as a few more trivia facts under their belts.
Our world today is plagued with environmental degradation that is occurring at an ever-growing frequency. Nearly every month on the news, we are not only exposed to the intensity of overfishing in coral reefs, but also the number of coral habitats destroyed by ocean acidification. As of today, over 200 coral species are threatened with extinction. But why? Do coral reefs really play a significant role in our lives? Accordingly, I've always been intrigued at how studying the coastlines can help us to forecast weather patterns, analyze human-environment interaction, and quantify the short and long-term impacts of man-made events. Coral reefs are known to be one of the most diverse habitats in the world and play a major factor in helping our environment. From protecting coastlines from dangerous storms to maintaining marine ecosystems and providing a habitat for coastal fisheries, coral reefs live up to their name as a rainforest of the seas. Hence, we chose coral reefs to not only educate our audience on what role these ocean habitats play, but also to inform our audience that astronaut photography can be the best place to start in our search for answers. With growing ocean acidification, rising sea temperatures, and overfishing, coastal reefs will see major changes in the coming decades unless we act now to preserve our environment. Through astronaut photography, we are able to not only identify potential hazards to coral reefs not seen elsewhere, but also find trends to how reefs all around the world are impacted uniquely to human behaviors. Ultimately, it is important to research and delve deep into astronaut photos of coral reefs to study the effects that climate change has on these beautiful coastal habitats.
Canyons are very unique and hold more information than what meets the eye. Canyons are carved by elements over millions of years and are usually found along mountain ranges, rivers, and coastlines. It is important to analyze photos about canyons because they can determine the age of geographical locations, signs of erosion, and how the surrounding environment is susceptible to change over time. Therefore, my teammate and I decided to pick canyons and reefs as our subtopics, so we could highlight the useful qualities they hold to observe now and prepare for the future. One challenge that my partner and I faced was finding the most practical software to create our interactive game. We decided on using PowerPoint and Canva because it allowed us to manage our time between researching and assembling the interactive. Another challenge was making sure that our interactive was appealing to K-12 students. We overcame this by brainstorming ways to make it more enjoyable and decided on adding lively colors, graphics, and useful hints.
After seeing our extensive project guidelines, we took to planning and sketching a template of our PowerPoint with respect to our subtopics. Through collaborating and bouncing ideas off of each other, we were able to effectively manage our time to create a presentation that encompasses multiple perspectives. From looking at previous research to thinking in the minds of our audience, we took steps to add depth and a pleasant aesthetic to our project. After going through a multitude of astronaut photographs, we narrowed our findings and picked 30 photos we concluded best showed not only significant geological features, but also photos that thoroughly emphasize multiple variables so we can share the potential of astronaut photography. Also, through our use of Google Earth, we were able to indicate to our audience the north direction on our photos for a better overall analysis of the images. Overall, through the experimental design process, we started with a solid goal in mind, listened to each other's feedback, and approached problems with an open mind, ready to tackle issues one step at a time.
Now I'm going to give you a brief walkthrough of the Where in the World interactive for canyons. Let's look at the first question. With this photo, the first thing that we can notice are a lot of white fluffy areas dispersed around the photo. This indicates that this canyon is located in a mountainous area and the mountains have snow on top. Let's look at the hints. The first hint says that this canyon is located in South Asia, and the second hint says that this is an ancient canyon buried along the Yarlung-Sangpo River in South Tibet. With these two hints, we can rule out the coastal canyons because those are located in Africa, not South Asia. We can also rule out the Sharan Canyon because it is located on the Sharan River. That leads us with our correct answer, the Himalaya Canyons. Did you know, after the geologists and the researchers discovered the ancient canyon, they dated the Yarlung-Sangpo River back to about 3 million years ago prior to the Himalayas. Let's look at one more question. With this photo here, we can see on the left-hand side that there were clouds in the atmosphere when the astronaut took the shot. In the middle right, we can also see the squiggly line that indicates that this canyon is located on the river. Let's look at the hints. The first hint says that this canyon is located on the border of 2 US states, and the second hint says that it is on the Green River. Knowing these two things, we can automatically rule out Canyon St. Anne and the Alto Toroni Volcano Canyons, because neither of those canyons are in the United States. That leaves us with the Flaming Gorge as our answer. Did you know, the Flaming Gorge got its name from an expedition in 1869 that explored the Green and Colorado rivers. Major John Wesley Powell and his crew thought the gorge looked like it was on fire from a distance. Thank you for going through that walkthrough with me.
Now let's look at an example of a Where in the World question with coral reefs as our subtopic. The idea behind these questions is to make the audience not only engaged, but also to make the question difficult, so the player has to delve deep into the photo and interpret different landforms. As shown here, we see that there is a bright, pristine lagoon near the Pacific Ocean with a kangaroo-rich environment, according to the hint, which allows us to come to the conclusion that this reef is located in Australia. Through the Did You Know fact provided after each correct question, the audience is educated with fun facts about the photo's location. Overall, this interactive is a colorful way to better people's data interpreting and visual analyzation skills.
Through the gamification of information about these geographical features, we hope to capture the attention of our youth and spark interest in space and STEM careers. We are currently in the process of converting our interactive slides to a medium known as Storyline 360, where we will be able to integrate our activities into the NASA website to reach a broader audience. Throughout our educational experience, we were rarely exposed to the plethora of NASA resources open to the public. By creating this interactive game, we want to educate and make these resources more accessible for the next generation. Throughout my NASA SEAS experience, I found my favorite parts were the activities that encouraged teamwork and innovation. Through these challenges, I was able to form connections with my peers while learning about their unique backgrounds and perspectives. The SEAS internship also showed me how much variety can be found in STEM careers and NASA specifically. In the future, I plan to continue employing the skills I have developed through this experience in my day-to-day life.
What I enjoyed most about being a NASA SEAS intern was getting to connect with my team. I haven't had any STEM experiences as immersive as this in a long time, and it was exciting being surrounded by people with a shared interest in science. This internship was invaluable in clearing up some of my uncertainties about what it means to work in STEM.
Being a part of the NASA SEAS internship didn't make me feel more secure or more sure about what I want to do in my future. Rather, it opened new doors for me that I hadn't even realized existed previously. The opportunities I learned of during this internship and the people I connected with created experiences I will remember for a lifetime, and ones that will no doubt have a positive, permanent impact on my life.
The best part about SEAS was not only the relationships I built with people here, but also the opportunities given to me. I learned more about myself and what I want to do with my future.
Partaking in the NASA SEAS program broadened my overall perspective of STEM. Through building parachute vehicles to controlling and programming speedboats with my team, I was able to engage and collaborate to solve fun and intricate problems to create innovative solutions. Overall, this experience has not only given me insight into the intricacies of global issues and the countless avenues for innovation, but also the mediums through which I can develop viable solutions. Because of SEAS, I'm enthused to tackle challenges, seek different perspectives, think critically, and bring my ideas to life.
My favorite parts about being a NASA SEAS intern were connecting with new people, learning about the various professions that NASA has to offer, gaining knowledge for my future, and making so many memories. I encourage anyone who enjoys STEM to look into this internship. It is an amazing opportunity.
We would like to dedicate our work to our mentor, chaperone, and the SEAS staff.
We appreciate all the time and effort you put in for us to succeed.
These 2 weeks have been an incredible opportunity. We couldn't have done it without you all.
Thank you to UT Austin for hosting us and providing accommodations.
Also, thank you to the Center for Space Research for providing us with cutting-edge facilities.
And finally, a thank you to NASA, SEAS, and the Texas Space Grant Consortium.
Great job. So we invite all of the interns to turn on their cameras from the astronaut photography group and to unmute. We have several questions for you. The first question is, what were some of the challenges that you faced when you were designing and making your interactives?
Yeah, so I can answer this one. So some of the challenges we faced revolved around the fact that we had to find engaging photos with key features that would help portray the full scope of astronaut photography. So using NASA's website called Gateway to Astronaut Photography, we sorted through a plethora of photos to find ones that would appeal to our audience, but also showcase what astronaut photography holds. And another quick challenge that we faced was to make it engaging enough for our youth so that they can actually be engaged in our interactive, but also educated. And we also wanted to make it valuable and worthwhile for our older audiences so they can also learn from it and benefit from our research.
So what are the next steps towards integrating the interactives into classrooms or citizen science projects?
So the next steps, like we said, that we're looking into are transferring the projects that we've already made into softwares like Articulate or Storyline 360, which basically allow us to turn what we have right now, which is essentially like a shell or a framework, into a more fleshed out and more responsive product that is ready to be released into classrooms and ready to be used. So that's our next plan for our project specifically, but then looking into astronaut photography itself, I guess the heart of our project was to look at how we can take this medium of astronaut photography that's kind of been underlooked for so long and tap into its potential a little more. So we also have plans for that as well, which just involve making it more accessible, not only so that younger people can experience it, but also so that it's ready to be shared, and it's more of a widely known resource that can be used in classrooms.
So how easy or how difficult was it to search for photos through the Astronaut Gateway?
I can take this one. So for some subtopics, there were already established collections available. So when searching for crater photos, for example, I was able to search through the crater collection, but there's still a lot of craters located. One handy feature was the map with pinpoints on it, and I could click on a location and see all the photos on the database of that crater. As for the others, can't speak to their experience, but there's a lot of photos on there. It was a little overwhelming at times.
And then how does your research help in understanding climate change?
So kind of looking at these astronaut photos, we can see over time there are certain trends that pop out to us in terms of climate and weather patterns. And these unusual events are something that these astronauts can pick up on and take photos of. And that's kind of one of the main ways that we can use astronaut photography to look at climate change.
And then what type of camera or software or tools are necessary for doing astronaut photography and analyzing that from Earth?
So from what we know and what NASA has released, they've been using Nikon cameras from the ISS, and these are pretty advanced digital cameras. However, they're also the same ones that we would see like professional photographers using here on Earth. So it's nothing really too crazy. And besides that, we really do use like the Gateway for Astronaut Photography quite a bit as a database that is open to the public.
Great. Well, you did an amazing job. I appreciate you sharing your research. And we will be preparing now to take a break. We'll be watching some of the highlights of the Earth and Space Science course that was prepared by Teresa Howard and Asha Karmaker. And we will return with student presentations at 4:25. So enjoy your break and enjoy these highlights. So welcome back to the NASA SEAS Science Symposium. Our next presentation is from Measuring the Environmental Changes with Altimetry Teams. Interns examined altimetry products and parameters over a wide range of global surfaces, including ice sheets, sea ice, vegetation, and ocean from 2 Earth-observing laser satellite altimeters, the Ice Cloud and Land Elevation Satellite, ISAT, and the ISAT-2 missions. A special thanks to their project mentor, Christine Smirda, for her leadership and guidance. Please join me in welcoming the first ISAT team and their project, a remote sensing approach to inland water volume prediction using long-term memory machine learning.
Hello everyone, we're the Hydrological Analyses Group from the NASA SEAS ISAT-2 research team, creating lake volume prediction for water management. I'm Priyanka Saprajabalaji. I'm a rising junior from San Jose, California, with an interest in remote sensing, machine learning, and data analysis. I'm interested in using geospatial tools and data visualization tools to observe data trends and participate in conclusion studies.
Hi, I'm Danny Hagenwalker from Miami, Florida. As a rising junior with interest in computer science and engineering, I spend time working on STEM projects that will foster my passion for learning and have the potential to make real-world impact.
Hi, my name is Wima Usa, and I'm a rising senior from Katy, Texas, with an interest in earth science, remote sensing, and engineering design. I'm curious about the development and usage of aerospace technologies and what we can learn from them.
What defines water scarcity? At what point in time should water managers expect water to reach a critical level where populations can no longer make use of their local natural resources? How much clarity do we have on future lake water levels? Today, we set out to discuss how we used ISAT-2 data to predict yearly water volume changes for inland California reservoirs.
On September 15, 2018, NASA launched the ISAT-2 mission. ISAT-2, or the Ice Cloud and Land Elevation Satellite, is an Earth-observing altimetry satellite which provides multi-year data to measure water elevation, ice sheet mass balance, cloud and aerosol heights, as well as land topography and vegetation characteristics for locations all around the world. ISAT-2 is a follow-up of NASA's previous ISAT mission, meant to record extremely accurate elevation levels.
ATLAS is the advanced topographic laser altimeter system that is on board ISAT-2. This is the instrument that sends out the LiDAR pulses to detect the signal photons. In our project, we use ATLAS 3 and ATLAS 8 datasets to measure elevation in inland reservoirs.
Reservoirs are artificial lakes constructed by the implementation of a dam to regulate water flow. Communities utilize reservoirs as major sources of electricity, water access, and recreational activity. As a result of the drying climate, the National Integrated Drought Information System indicates that approximately 85.4% of California is experiencing severe drought conditions. This has ultimately led to a decrease in the lake reservoir volumes and the exposure of shorelines. Such effects can have negative impacts on the surrounding communities and the environment, such as in precipitation, irrigation systems, real estate, and hydroelectric power plants.
To investigate the water level problems in California, we referenced 10 of California's largest reservoirs. Using ISAT-2 elevation data from Open Altimetry and data from the California Department of Water Resources, we confirmed that there is an apparent yearly downward trend in the water level of lakes. However, the rate of decrease was not clear. The Global Surface Water Explorer map images showed this water level decreasing and an increased shoreline exposure. In addition, water managers are unable to provide long-term predictive analyses for the trends in water loss, which leaves cities unprepared for future water problems.
We discovered that similar water level trends could be identified in more than 40 other California reservoirs. Throughout our research, our goal was to use Python scripts to create an efficient, repeatable, and automated process to source, download, and process ISAT-2 data. This allowed us to broaden our scope beyond just a few reservoirs and study over 40 different bodies of water, and calculate each of their water volume losses over a 2-year period. We also hope to utilize this data in order to create machine learning models that predict water level changes a few years in the future. We hypothesize that there will be regional trends in water levels that will help water resource managers better understand the yearly water level fluctuations in California.
The research process began by collecting and processing the ISAT-2 data. In Open Altimetry, we were able to collect the ATL03 and ATL08 track data for Lake Shasta and other California reservoirs, visualizing the data in a graph. Using the National Snow and Ice Data Center, we were able to download the ISAT-2 track data as an H5 file, later using PhoReal, or the Photon Research and Engineering Analysis Library, to convert our data into CSV and KML files that we could use in the machine learning process, as well as when working with QGIS. To facilitate data collection and in the interest of creating a repeatable process accessible to anyone that could be further scaled across the entirety of the United States, our team utilized the power of a multitude of openly available resources. Primarily, we made use of Python scripts that served as the backbone for our data collection procedures by querying the NSIDC website for ISAT-2 tracks.
By looking at lakes and reservoirs spread out across California through the lens of remote sensing satellites, ISAT-2 and Landsat-8, we were able to gain insightful information on the regional trends in the United States. We then fed this information into a long short-term memory machine learning model trained with water level measurement data of 5 lakes. By accounting for the natural sinusoidal fluctuations that occur due to seasonal changes and weather events, this machine learning model accurately predicts water levels years in advance. In effect, this served as the bridge between studying the annual fluctuations of the water level and identifying the overall regional trends and creating accurate water level predictions. The long short-term memory machine learning model, also known as the LSTM model, is a recurrent neural network layer that enables support for time series and sequence data in a network. It performs additive interactions which can help improve gradient flow over long sequences during training and is best suited to learn long-term dependencies. It was developed using Python on Google Colaboratory. It predicts a change in water level for lakes for more than 5 years and outputs predictions as a graph.
There were 4 steps in the process to train and use the LSTM machine learning model. In the first import step, we imported data from the lake statistics websites and stored them as CSV files on the computer. We imported this data into Colaboratory and graphed it. In training the model, we standardized our inputs and used 2 layers to process the data, the LSTM layer and a dense layer. During the testing phase, we input past water statistics from other lakes in California, for which we knew the accurate water levels, and noticed a high accuracy and decreased error over time. In the prediction phase, we inputted future times and generated a graph showing the predicted future water statistics for an individual lake. This information could be circulated to water managers in order to make informed decisions concerning the lake. Here, we show our model's prediction capability based on past water statistics. On the left, we have the given data for a few California lakes for the first 1,000 days. On the right, we have the predicted data for the same lakes as predicted by the model. One of the lakes we considered was Lake Shasta. Lake Shasta is a reservoir located in Northern California and supplies water resources for Sacramento, Redding, and other nearby communities. The data for the first 1125 days followed a downward sinusoidal trend. The current average water volume of the lake is 1,700,000 acre-feet, and the machine learning model predicts the water volume to reach 1,200,000 acre-feet after 5 years.
Another lake we considered was Lake Trinity. Lake Trinity is a reservoir located in Central California and supplies water resources for Monterey, Salinas, and other nearby communities. The current average water volume of the lake is 2.4 million acre-feet, and the machine learning model predicts that the water volume will change to an average of 1.9 acre-feet after 5 years. The procedure required to convert satellite imagery and altimetry data was largely automated by scripts written in Google's Colaboratory and QGIS's PyQGIS. QGIS is an open source software for creating, editing, visualizing, and analyzing geospatial data. This multi-step process started off with water occurrence maps derived from the Landsat suite over a 40-year period that covered nearly 5 million square miles of the Earth's surface. Distinct lakes were clipped and extracted by drawing bounding boxes around the areas of interest, and then turned into vectors and shapefiles from raster images to begin data processing. Using these shapefiles, along with the longitude and latitude data stored in a given ISAT-2 track, we were able to define intersection points between the lake and ISAT-2's path, enabling us to sample up to 100,000 points of elevation in a given lake, and gain an accurate water level measurement at any point in time. In addition, the shapefiles were useful in calculating the area of lakes due to their accurately projected geometry on an EPSG 4326 world projection. At its worst, we expect an error of only 4%, which is small enough that it had negligible effects on our final outcome. After measuring water height change and calculating the surface area of each lake, The volume loss calculation was fairly simple.
Over the course of our project, we faced a series of challenges that we had to overcome with perseverance and a little creativity. To begin with, the data collection process was inefficient since ISAT-2 tracks are stored in very large files, which became hard to process. Working with nearly a terabyte of data, we had to come up with creative ways to break up the data and reduce processing time. In addition, since the data followed a diagonal sinusoidal pattern, it was initially difficult to choose a machine learning model which could accurately predict future water statistics based on past data. However, after doing a substantial amount of research on the topic, we were able to determine which model we wanted to use. With regards to QGIS, we were initially hesitant to manually process such large amounts of data, which prompted us to begin investigating ways to use QGIS's native Python scripting platform. Since tracks would oftentimes pass over river systems whose downstream flow would cause discrepancies in water height calculations, defining intersection points proved to be a necessary step in ensuring we avoided including land elevation in our water measurements. In addition, we only considered the most voluminous part of the lake, which would provide the most accurate measurements representing the true water level of the lake, independent of major elevation differences introduced by natural flow of river dynamics.
The combination of ISAT-2 track data and Landsat-8 has proven to be a useful method of calculating water level volume loss and making predictions about future loss. The graph on the left shows large red circles that indicate loss in water levels in a lake. As seen in the figure, water loss is evident throughout all of California. We also concluded that on average, there's a large correlation between lake location and water level decreases across California, which is consistent with our model's prediction. We believe that the accurate conclusions of our graphs and figures from this research can be extremely helpful to water managers to understand the potential change in size of their lakes for years in the future.
Moving forward, we are confident that with our machine learning model and Python scripts, we can apply our process to reservoirs across the globe. We can efficiently collect the data and make accurate predictions about water volume loss in the next few years. As of now, we are looking into combining our accurate data modeling predictions with more complete information, such as factoring in precipitation levels by El Niños and La Niñas, as well as the community's usage of the reservoir. We also want to understand which populations are dependent on certain reservoirs and to what extent. All of this could be achieved by accessing the available data that is recorded for these factors.
NASA SEAS has been a STEM enriching experience that has provided us with immense opportunities. I came into NASA SEAS simply with an interest in learning about Earth and space science. However, my time in this program has allowed me to explore new possibilities in these fields, as well as expand my knowledge in new areas like aerospace engineering and astrobiology.
Prior to the NASA SEAS experience, I was unaware of the vastly diverse career opportunities that NASA has to offer. Simply by listening to various different experts speak, working closely with a project mentor, and meeting so many different people, all that share similar interests as me, I know I have just scratched the surface of a field I'm eager to explore.
NASA SEAS gave me the opportunity to conduct authentic research on real data sets alongside a mentor, which will equip me for advanced research projects in college and in other NASA internships. The experience of working alongside NASA experts, scientists, and engineers inspired me and opened my mind to view the multiple dimensions of a career in aerospace, computer science, and other Earth studies at NASA. We especially want to thank our mentor, Dr. Samarda, for guiding us through the research process. Her passion and dedication ensured the project's overall success. Her helpful guidance along the way was significant to the advancement of the project. We would also like to thank everyone for your time, and we look forward to answering your questions. Thank you.
Great job. And we have several questions for your team. What would you say, first of all, I want to say, please turn on your cameras for those team members and unmute your mics. What would you say is the biggest issue while you were collecting data and processing automated data?
Right, so I guess the biggest issue I'd say we ran into while creating the automation process was when working with the NSIDC website, which is where all of the ISAT-2 data is made publicly available. One of the main problems with how this data is stored is that when our Python script would make a request or query the website, we would find track files that, although they matched our description, when they were downloaded, they came back as tracks that covered the entire extent of the globe, as opposed to the restricting geographical bounding boxes that we had determined. And further along the process, this caused many integration issues, as these files were getting way too large to download and process, breaking up the workflow that we had established. I guess I'll add that although we weren't exactly able to solve this problem, given the short 2-week window we had, moving forward, it's certainly something that we're looking into finding a solution for, and mainly in the interest of creating a fully automated process that is scalable across the world. But yeah, to answer the question, I would say that we ran into a data size issue, which ended up being the biggest problem we faced, as it affected the chain of automation.
During your project, did you look at multispectral satellite imaging of the lake areas to improve your calculations? Or did you not have time to include that in your project?
So I would say we used a product from Landsat, the Landsat suite, which was water occurrence maps, and I'm forgetting now exactly how those are derived, but I'm pretty sure it takes visible imagery, which is multispectral, and combines it to detect where water is, where water has been found over about 40-year period of time. So I would say that the thing that would probably be the most beneficial for the accuracy of our data would be imagery that is sectioned off by year, as opposed to a more broad 40-year time span, which would give us more accurate area calculations based on different times of the year, or sorry, not different times of the year, different years.
So I know that in this project, you chose to study reservoirs in California. If you had more time, what other bodies of water or regions would you want to study?
So we actually chose California because most lakes in California, when we actually individually analyzed them, had shown the most largest water volume decreases. So especially since California has been in a state of drought for quite a long time, we felt that the water managers would also find future trend data based on past decreases to be most useful. So they're actually able to take the necessary action before there's irreversible conditions. In the future, we're actually considering to go over trends in reservoirs in states like Arizona and other desert states, which usually utilize water from out of state or just have few water resources.
And how did you convert water surface area into water volume?
So basically, with a simple formula, we were able to calculate the water volume loss of the lakes over a 2-year period. So yeah, we used QGIS to find the surface area and calculate the intersections between the lake area and the ground area, and then multiplied that by the change in the surface height of the lake to be able to find the volume loss.
And what was the most surprising or interesting NASA career that you were introduced to during the SEAS internship?
Maybe for me, the most interesting NASA career was working with robotics and helping develop the different tools and rovers that they use on other planets. I thought that was really interesting and pretty cool to be have an actual part in the space exploration.
So during our visit to Johnson Space Center, what did you find most interesting?
At least for me, there was a brief point in time for maybe 5 or 10 minutes where we got to see a lot of people just going about their day, working on their computer, and they're all in this dream lab, it looks like, And just based on the limited engineering experience that I've had, it's really cool to see the potential that's out there.
And why did you choose to use an LSTM model instead of any other ML model?
So with the long short-term memory machine learning model, we chose that one mainly because it performs better for time series forecasting. And unlike other like regression models or other polynomial regression models, the LSTM model has a dense layer which can more accurately predict the future values based on previous data that isn't necessarily sequential. And essentially, it's able to capture the non-linear relationships between the variables, which means that it can fit non-linear data, especially like downward sinusoidal data better.
Well, you did an amazing job and congratulate you all on your research. Our next team is the ISAT-2 team with their project and inquiry into sea ice thickness and penguin population.
Hello, fellow researchers, scientists, family, and friends. Welcome. We are the ISAT-2 group measuring sea ice extent utilizing altimetry. Hello, my name is Ahmed Deeb, and I am a junior from Ormond Beach, Florida. My hobbies include playing basketball and volleyball, taking pictures, as well as listening to music. My future aspirations include entering the medical field one day, as well as continuing conducting climate research.
Hi, I'm Spence Cox, and I'm a senior from Charleston, South Carolina, where I enjoy kayaking and playing ultimate frisbee. I'm passionate about climate research and renewable energy development, and I hope to become a mechanical engineer in these fields.
Hello, my name is Ayushi Kashyap, and I'm a senior from Fremont, California, where in my free time I enjoy biking, reading, and exploring the outdoors. I also enjoy exploring the intersection between data analysis and climate science, as well as how Earth's processes shape our world. In the future, I aspire to work in the data science field.
Our research question for our research is evaluating the association between ISAT-2's derived sea ice thickness and freeboard with penguin populations in Cape Washington, Antarctica. The satellite that we focused our research on is ISAT-2, which stands for Ice, Cloud, and Land Elevation Satellite. Its launch date was September 15 in 2018, and its satellite mission is to use its onboard laser altimetry system to measure developments in the cryosphere. This is super important because this allows scientists to develop alternative sustainable solutions. On board of ISAT-2, it carries a singular LiDAR instrument, which is known as Atlas. It fires 6 photon beams, 3 weak and 3 strong, and 2 products that we specifically focused on in our research is ATL-7, which focuses on sea ice height as well as open water leads, as well as ATL-10, which focuses on estimates of sea ice freeboard. In figure 1 is the ISAT-2 satellite in orbit, as well as in figure 2, it represents the pulses of light that goes through mirrors and lenses. They go through this process before hitting the ground to ensure that the timing, size, and position is perfect, and it is split up into 6 beams. In figure 3 is a Virion telescope, which is shown with the addition of the laser reference system, which serves as a steering device with the overall purpose of catching photons.
We extensively use the Landsat 8 satellite, the 8th in the program. It has 2 main instruments, the operational land imager, which has 9 bands in the shortwave infrared and visible imagery, and the thermal infrared sensor, which has 2 bands of thermal data.
The following table compares both satellite systems that we mainly use in our research, which are ISAT-2 as well as Landsat 8. ISAT-2 is a LiDAR altimeter with a spatial resolution of 70 centimeters, as well as a temporal resolution of 91 days. Landsat 8 has 2 types, a visible and thermal sensor. For visible, it has 15 meters of panchromatic bands as well as 30 meters of the rest of the bands. And the thermal sensor has a 100-meter spatial resolution. Its temporal resolution is 16 days. And how we used both of these satellite systems was for ISAT-2, we used it to calculate the sea ice height and thickness, and for Landsat-8, we used it to quantify the sea ice area.
There has been high fluctuation in Antarctic sea ice extent. However, it has grown in the past 40 years, but there has been an extreme low in 2017. The emperor sea penguins heavily rely on the sea ice for a breeding ground and to support krill populations, which is the base of the food chain. However, climate change models predict that all emperor penguin populations will be quasi-extinct by 2100.
The colony we chose to study was Cape Washington, located in Antarctica. The longitude is 165.42 degrees, and the latitude is negative 74.65 degrees. Some of our goals with this research project is to 1. Predict the future penguin population of Cape Washington, as well as unearth the association between sea ice volume and penguin population, and finally, on a global scale, analyze and predict the sea ice changes in the Antarctic region.
The global climate crisis poses a serious threat to mankind, species loss, and habitat destruction. Antarctica has seen significant influence from this, as the poles are affected more than any other place on Earth. The decrease in sea ice has a great effect on the animals present in this area.
The research objective is to measure the changes of sea ice thickness as well as sea ice freeboard through the utilization of ISAT-2 and how it affects emperor penguin colonies in Cape Washington. As you know, sea ice melting has burdened the scientific world for a long time due to its adverse effects. So we hope that our research will allow us to make connections and discover when sea ice thickness and freeboard is at its highest. And with this, we can better understand what we need to do to help maintain these conditions.
The dates we chose to research in this study include 2 dates from each month, October, November, and December from 2018, 2019, and 2020 from the ISAT-2 and Landsat-8 satellites. The reason we chose these dates are because it's during the spring season in the Antarctic region, meaning that the sea ice is at its highest, as well as it being the emperor penguin's hunting season. Our hypothesis is that as a result of the greenhouse effect, greenhouse gases trap sunlight in the atmosphere, causing higher global temperatures, and respectively, we hypothesize that there will be a decline in the sea ice thickness and freeboard due to the absorption of solar radiation. Therefore, the emperor penguin colony in Cape Washington will decrease due to the declining sea ice, which leads to a diminishing food source and loss of habitat.
It's important to understand the true extent of sea ice. While just the freeboard is shown, or the part above the top of the water, sea ice often extends far below this because of the interaction of ice and water.
Below are 2 images from Cape Washington, Antarctica. These images were taken both on October 25th. The one on the left-hand side is from 2018, as well as the one on the right-hand side is from 2019. Just for a little background, we couldn't use the images to its full capacity due to the images not intersecting correctly. Therefore, we used QGIS as a platform of finding the overlay as well as the intersection between 2 images. Next to the images, we have a short animation of a 1-year lapse to see the sea ice change. As we can see on the northwest side, we can see that the water mass is decreased from 2018 to 2019, as well as there is a buildup of sea ice extent. Therefore, this serves as evidence that there was a sea ice buildup from the years 2018 through 2019. We will now be talking about the way we acquired, extracted, and processed our data, as well as the overall methods of our project.
We use Python for scripting and QGIS as a free software for classification and visualization. We use the read ISAT-2 package to find the sea ice height, and pandas and matplotlib for data processing and plotting. We pulled the best tracks from the National Snow and Ice Data Center by selecting the correct coordinates and times. We pulled these files into Open Altimetry to check for ATL 10 points. And then we chose the correct tracks from October to December from 2018 to 2020.
In order to extract the data, we used multiple Python packages, but most specifically, we used the ATL07 and ATL10 ISAT2 packages created by the science team. We sampled specific data attributes to process these. On the right, we have an example of some of the packages that we imported, such as matplotlib, pandas, and as well as the ISAT2 toolkit. This is the full code from our extraction script, which read in the ATL10 file and extracted the attributes listed in the middle in green.
On Python 3, we used the package readISAT2 to obtain the sea ice heights and to process the H5 files. The package has a variety of scripts that are used to read the ATL beams and files, and it converts the beams to formats. It's also used to create all of the masks.
This is our full code to process the already extracted data. It includes parts to cut the data shorter based on the latitude of the data products, as well as filtering through the based on some factors such as null values, and then converting the freeboard height to sea ice thickness based on the formula.
The attributes that we chose to analyze and extract included the latitude, longitude, height segment height, beam height, and much more. The geolocation data was provided by the latitude and longitude coordinates. The height segment height attribute provided the geolocated and absolute height of the freeboard data. The height segment confidence provided us the confidence interval to corroborate the accuracy of the data. The height segment type attribute provided us information about the type of sea ice. And the height segment flag attribute provided us information of whether the freeboard data was the ice level or the sea level. And arguably the most important attribute, the beam height attribute. It provided us with the freeboard height of the sea ice.
In order to process the data, we cut the data to restrict all of it to a specific range of latitudes based on where the beams travel in the area. We figured this out through the Open Altimetry website. From that, we specifically took the beam FB height attribute from the extracted data CSV and modified this freeboard height to calculate the sea ice thickness. The original data contained multiple values that were null and were represented by an abnormally large number, so we filtered through those to remove them from the file. The top screenshot shows the cutting down of the data based on the latitudes, and the bottom screenshot shows the modifying of the freeboard height to calculate the sea ice thickness. In order to calculate the sea ice thickness, we explored a variety of methods. The one we settled on is the sea ice thickness equation that takes into account the difference in density between seawater and ice in order to calculate the sea ice thickness below the water's surface as well as above the surface. This equation is h sub I, which is the sea ice thickness that we want to find, which is equal to rho sub w, which is the density of seawater, over rho sub w again, minus rho sub I, which is the density of ice, multiplied by h sub f, the freeboard height extracted from the beams. The coefficient of the freeboard height density ratio came out to be equal to 9.9029, which we hard-coded into our script. In result, we cycled through the extracted freeboard heights to create a new data column containing the sea ice thickness. On average, the sea ice thickness over the 3 years, 2018, 2019, and 2020, did vary by a bit, but not by a whole amount, trending at around 2 to 3 meters thick.
The graphs below show the sea ice thickness over time. We utilized 3 years, 2018, 2019, and 2020. So let's go ahead and look at the graphs. During 2018, the sea ice thickness was relatively steady, and this is actually the only year that the trend line was increasing. During 2019, we see a massive increase in the beginning of October with a massive decrease in the middle of October, as well as an increase at the end of December, but later on in 2020, there is a large decrease in early October. And during 2020, in the middle of October, we see a large increase in sea ice thickness, and it decreases in the middle of November. And the trend lines for 2018 and 2020 are decreasing. Listed below, we have two graphics analyzing a comparison between 2 years. On the left-hand side, we have a graph showing sea ice thickness over the years of 2018 through 2019. On the right-hand side, we have a comparison of sea ice thickness for 2019 through 2020. By analyzing these graphs, on the left-hand side, we see our lowest point of sea ice thickness between the 2 years happens during early November in 2019, with our highest point of sea ice thickness also in 2019 during early October. When we shift gears to 2019 and 2020, we see that our highest point is during 2019 and early October, with our lowest point in early October for the year of 2020. Analyzing these graphs, we see that there is a bit of a trend between the Antarctic spring months. In early October, we see a massive decrease of sea ice thickness where it stays relatively steady until December, where we see an increase. However, surprisingly, in the year of 2020, we see a delay and sea ice thickness doesn't increase in the months of December, it actually decreases.
Here we show a graph of the sea ice thickness from 2018 to 2020. It shows a comparison of all the years of our study. And as seen, there's a slight trend down from 2018 to 2020 on overall thickness. To find the sea ice extent, we put the files into QGIS. We then classified these files by adding in a training input in which we told the computer which files were sea ice and which points were not. The computer then classified the entire image. And as seen here, all ice is in green and red, and sea ice is thin closer to the water. We also applied a mask for the land so that the ice here would not be considered sea ice.
We took clear Landsat 8 visual imagery of Cape Washington collected from the United States Geological Survey to start our classification. We then imported the data into QGIS, where we took land masks of the separate ice sheets and training inputs for all the classes. We then were able to report the yield surface area of ice for each month, which is located in the table below. In order to calculate the sea ice volume, we took the average height from each date from each month to calculate the volume based on the surface area that we uncovered in the previous classification. We figured out that the volume stays consistent relative to each other between the 3 years over the 3 months. However, there is no significant change from year to year, as well as no prominent year-to-year trend, which is good because this doesn't show any dire changes in the sea ice volume. However, we did notice that the sea ice volume is declining during the late spring month of December, which is located in the graph to the right.
The short intersection between ISAT-2's datasets as well as Cape Washington's population counts only gave us 2 years of joint data. Using ISAT-2's datasets, we predicted the penguin population for 2020 based on sea ice extent and volume. Below is listed a timeline of the datasets that we've used for our research. This graph visualizes Cape Washington's penguin population through the years. As we analyze this graph, during 2011, the lowest point of penguin population occurred, with a total of 10,322 emperor penguins. As we further analyze this graph, during 2015, penguin population was at 24,997, but during 2017, there was a decrease of 12,525 emperor penguins. This directly correlates with the lowest time of sea ice thickness in recorded history of Antarctica. As we further analyze this graph, during 2018 to 2019, the penguin population started to decrease again.
Some of the challenges we faced included visualizing Cape Washington sea ice through QGIS, as well as creating masks on the actual visual imagery itself. We also faced the challenge of interpreting the unprocessed data to account for any missing factors including figuring out and processing the data to optimize it with the best equation.
For our study, we have concluded that there is a downwards trend in the sea ice extent, sea ice height, and sea ice volume from 2018 to 2020. We support the idea that emperor penguin population is strongly correlated to the amount of sea ice in the area. Our study provides critical context to understanding the risks that threaten these populations.
As we further our research, we would like to expand our horizon, possibly researching towards the northern hemisphere in Greenland, as well as improved monitoring of sea ice extent for climate change. We would also like to analyze the movement of colonies over time. This research is proven to be beneficial due to its impact of setting the foundation of sea ice during a long period of time, especially how sea ice thickness affects penguin population. We studied Cape Washington, where emperor penguins are at its highest. Scientists can use this research to find the optimal conditions where sea ice thickness as well as penguin population are at its highest. The SEAS internship has provided us with many new opportunities, as well as will serve as a lifelong memory. The SEAS internship allowed us to meet new people from across the nation, as well as conducting fun activities. For example, we made a mousetrap car or spray painting the solar system, as well as listening to amazing and inspirational guest speakers. For example, we listened to past Apollo 13 astronaut Fred Hayes. In addition, we got to explore many new places, for example, like the Johnson Space Center, Six Flags, and a professional setting where we can conduct research. NASA SEAS gave me the opportunity to connect with like-minded peers around the nation and develop my research skills. I am so thankful to be a part of NASA SEAS and can't wait to utilize my skills in the future.
The SEAS program is a great opportunity to find specialized application of remote sensing in my areas of interest. I've had a great time in this program, and I've learned so much.
The SEAS internship has served as a memorable experience along with the lifelong friends I've made. I'm so thankful to be given this opportunity and to broaden my horizons as well as focus on the subject I would like to study in college.
We would like to extend our sincere appreciation to Dr. Christine Samerda for her support and guidance through the entire research process. We are extremely thankful for the lessons we've learned through this journey. We would like to extend a special thank you to NASA, the Center for Space and Research, the Texas Space Grant Consortium, and the SEAS program, as well as every single one of the mentors, administrators, Miss Miller and Miss Baggio, and chaperones who helped us take part in this experience. Below, we have our sources that we've utilized during our research. And last, but certainly not least, is our mission patch for our Sea Ice group. Thank you all for listening.
Great presentation. So I invite you to turn on your cameras and unmute. We have several questions for your team. The first is, was there anything surprising to you about the penguin populations that you studied? And if so, what?
I would have to say the most surprising thing about penguin population was actually what occurred during 2015. Previously, my group and I hypothesized that the penguin population would be at its lowest in our latest years, because as we know, the global temperatures are rising. And however, we actually found that during 2015 and 2017 were emperor penguin populations at its lowest in Cape Washington, with a decrease of over 12,000 emperor penguins. And after that, in 2018, penguin populations started to rise again. However, sadly, at the end of our data research, we found that penguin populations in Cape Washington started to decrease again.
So the next question is, how did you decide which attributes to extract in your Python scripts?
Yeah, so we decided the specific attributes to extract in the Python scripts by looking at the provided ATL07 and ATL10 dictionaries, which are basically the descriptions of the attributes produced by the product, as well as the ATBD, which is the theoretical basis document, which provided us with the knowledge to best analyze the data associated with these products.
And how did you perform the classification process on QGIS?
Sure, so we performed the classification by inputting the pictures, which we then added training inputs to, which is where we told the computer which parts of the picture were sea ice and which parts were not. And then after the computer classified the entire sea ice around Cape Washington, we actually clipped out the parts that were just the ice sheet so that they wouldn't be counted into sea ice as well. And then when we had classified all of the images over all 3 time periods, we actually found the intersection of the images because they are not taken at the exact same spot. So to find the areas that were in all of them and to find the equal surface area, we had to find the intersection and create a polygon, which we then drew a classification report from, which gave the total surface area of the sea ice and the not sea ice.
So I know that based on what I heard during your presentation, that you chose Cape Washington because of the large number of emperor penguins. So if you were to pick additional sites to study, what would you study and where?
If we were to pick, sorry.
That's a great question. As we were picking our location for our project, we were researching different areas in Antarctica that had a large amount of emperor penguin populations, and we found about Cape Washington. However, we actually looked into different colonies and areas that we were going to research. For example, there was Cape Gates as well as Cassie Bay and Yulee Bay. There's different areas around Antarctica. However, we decided Cape Washington fitted our research the best, with the best utilization of our ISAT-2 satellite with the clearest images, as well as a great amount of emperor penguin populations where we can conduct our research on.
Great. Well, it sounds really interesting, and I certainly learned a lot. So thank you all. The success of SEAS is determined not only by the commitment and research conducted by the student interns, but also by the commitment from their mentors and project assistants. To our NASA subject matter experts and project assistants, your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded. Selena and I want to thank you for your time and your talent that you shared with our student interns. And I know the student interns appreciate your guidance and advice as they conducted their research. So a big applause to all of our mentors, subject matter experts, and project assistants. So we want to thank you for joining us for day 1 of the NASA SEAS Science Symposium. Please join us again tomorrow at 12:30 Central Time as we continue to share the research from the NASA STEM Enhancement in Earth and Space Science High School Internship. Thank you.